Good morning. I'm Chuck Riley, Associate Dean for Academic Affairs in the College of Engineering and Computer Science. It is my pleasure this morning to welcome you to UCF and to our college's third annual Progress Energy Senior Design Symposium in Renewable and Sustainable Energy. The college's Senior Design Symposium in the clean energy sector became the first of its kind in America when it was initiated 3 years ago. You might ask, why should such a symposium be held at UCF? Our president, Dr. John Hitt, is a member of the American College and University President's Climate Commitment Leadership Circle. UCF has adopted the U.S. Green Building Council's Leadership in Energy and Environmental Design, or LEED standards, for our new and renovated buildings. Our ambitious climate action plan strengthens UCF's status as an innovative leader in green operations, academics, and research. This plan will guide the nation's second largest university as it works to meet President Hitt's pledge to become climate neutral by 2050. In keeping with the university's mission and commitments, the UCF Progress Energy Senior Design Symposium focuses on socially conscious engineering projects in renewable and sustainable energy. During their senior year, UCF engineering students bridge the gap between academic and professional experience by participating in year-long design and build projects, including many that involve renewable and sustainable energy. Along with their faculty advisors, engineering students work to develop innovative project proposals, analyze alternative designs, design and build a prototype, prepare engineering reports, and present their final work at the Progress Energy Senior Design Symposium. Along the way, our students gain valuable experiences in project management, leadership, and team building. This morning, our talented senior design student teams will be presenting executive summaries of their projects and showcasing their final designs in the exhibit area. We will have a series of presentations followed by short refreshment intermissions so you may personally visit each exhibit and discuss details of the projects with our students. Thank you for being here today and being a part of this showcase event. Now it is my privilege and honor to introduce Dr. Marwan Saman, Dean of UCF's College of Engineering and Computer Science. Dean Saman.
Thank you, Chuck. Good morning. Good morning, and welcome to the third annual UCF Progress Energy Senior Design Symposium in Renewable and Sustainable Energy. For 3 years in a row, this symposium has become a tradition for our students to present the results of their senior design projects in the area of renewable and sustainable energy. As some of you might know, our college is home to over 6,000 undergraduate students, making us the 9th largest College of Engineering Computer Science by enrollment in the nation. We have supplied and continue to supply the region with a talented workforce that is well prepared to meet the challenges that they will face in building a better world for all of us. Since the focus of this symposium is on energy, I am sure you all are aware that Central Florida region is steadily becoming one of the world's leading regions in R&D activities in renewable energy and alternative fuel endeavors. Orlando is home to worldwide industry leaders such as Siemens Energy and Mitsubishi Power Systems, and UCF and our college are home to the Florida Solar Energy Center and the Siemens Energy Center housed in our Mechanical Materials and Aerospace Department. The senior design presentation and exhibits that are on display today and the presentations that will be given later this morning reflect the innovation, creativity, and hard work of many of our best students in the College of Engineering and Computer Science. Applying classroom learning in solving real-world problems is something that we value very much in our college and strive to do very well at. This symposium is a great example of innovation and experience-based learning at its best. I want to take a moment to thank all of the students who are participating in this symposium today for the investment in your education that these presentations and exhibits illustrate. Let's give the students an applause to all of them. I also want to thank the faculty members and advisors to these projects for preparing the students and guiding them and mentoring them to complete these projects. Let's also give a hand to all the people who work behind the scenes. And also a big thank you goes to the symposium sponsor, Progress Energy. Progress Energy is a great friend of UCF and our college and has supported many of our important educational initiatives throughout the year. Thank you, Progress Energy. Also, I want to thank Orange County Mayor Teresa Jacobs and Orange County Economic Director John Lewis, who will be providing a special proclamation on behalf of Mayor Jacobs and Orange County for recognizing this UCF Progress Energy Senior Design Day in renewable and sustainable energy. Special recognition and thanks also go to our partner contributors to this symposium: Workforce Central Florida, UCF's Department of Sustainability and Energy, Harris Corporation, and EnviroBright. I just want to add that our hospitality sponsor today, EnviroBright, is a company that was founded by two UCF graduates, Mike Brennan and Jason Plurdy. It's now my pleasure to introduce John Lewis, Director of Orange County's Economic, Trade, and Tourism Development Office. John will present a special proclamation on behalf of Mayor Jacobs and Orange County. John?
Thank you, Dr. Simone. Whereas the University of Central Florida, the nation's second largest university, is a member of the American College and University President's Climate Commitment Leadership Circle, is an innovative leader in green operations, classes, and research, and is committed to developing socially conscious engineering projects, and whereas the third annual UCF Progress Energy Senior Design Symposium in Renewable and Sustainable Energy will showcase undergraduate engineering innovation and student talent developed from the College of Engineering and Computer Science as the next wave of engineers in renewable and sustainable energy. And whereas by investing in tomorrow's energy leaders today, UCF hopes to encourage the long-term development and adoption of efficient, reliable, and sustainable renewable energy technologies throughout the world, whereas our nation recognizes that renewable energy is an important part of the balanced solution necessary to meet our current and future energy security needs, and whereas Progress Energy is pursuing a balanced strategy for a secure energy future, which includes aggressive energy efficiency programs, investments in renewable energy technologies, and a state-of-the-art electricity system, and is committed to supporting and showcasing the next generation of innovation and talent at the third annual UCF Progress Energy Senior Design Symposium in Renewable and Sustainable Energy. And whereas Orange County recognizes the strategic importance of the human capital talent pipeline and the next generation of engineers in renewable and sustainable energy from the UCF College of Engineering and Computer Science as a vital contribution for the future development of the clean tech energy sector in Orange County and Central Florida, now therefore, I, Teresa Jacobs, by the virtue of the authority invested in me as Orange County Mayor, do hereby proclaim Friday, April the 8th, 2011, as UCF College of Engineering and Computer Science third annual Progress Energy Senior Design Symposium in Renewable and Sustainable Energy Day in Orange County, Florida, done and ordered this 8th day of April, 2001. Teresa Jacobs, Orange County Mayor. I read every word of that because I think every word of that is important. Simon, thank you for allowing me to be part of it.
Thank you, John, and thank you, Mayor Jacobs and Orange County, for your continued support of our College of Engineering and Computer Science. It is now my pleasure to introduce our keynote speaker for this symposium, Vincent Dolan. Please allow me to first share some background regarding Mr. Dolan. Vinnie Dolan is President and CEO of Progress Energy Florida, with operation in 35 Florida counties, serving more than 1.6 million customers. Vinnie assumed his role in July 2009. Since joining the company in 1986, Mr. Dolan has held a number of management positions in such areas as corporate strategic planning, commercial and industrial sales, energy efficiency, power quality, and business development. Most recently, he was responsible for Florida regulatory affairs, public policy, community relations, economic development, commercial, industrial, and governmental sales and service, state and federal public affairs, and energy policy and strategy. He serves on the boards of many community organizations, including the Board of Trustees of the Florida Chamber of Commerce Foundation, Old Children's Hospital, and Enterprise Florida, along with membership on the Florida Council of 100. He also serves on a number of utility industry organizations. A graduate of Rutgers University in New Jersey, Mr. Dolan holds a Bachelor of Science degree in Mechanical Engineering. Without further ado, Mr. Dolan.
Thank you, Dean.
Thank you very much.
Well, good morning, everyone. I have to tell you, it's very inspiring to me as a father of a college freshman to see so many young folks up and early and dressed on a Friday morning here at the university, so thank you for that. And I'll tell you, it's a pleasure to be here. I had the opportunity to be here last year, and I was excited to be here again this morning. Had a chance to see a couple of the projects, and I'm anxious to see the balance of them after my remarks, and always inspiring to see the innovation and creativity of our up-and-coming engineers, and congratulations to all of you on the work that you've done so far. You know, our company, Progress Energy, we're very proud of our partnership with the University of Central Florida, you know, especially as it relates to the energy education curriculum and efforts like this to develop sustainable and promising renewable energy technologies for the future. You know, we're also committed at our company to work very hard day in and day out on our daily mission, and that's to make sure that we're providing clean and reliable power to the 1.6 million homes and businesses in the state of Florida that depend on us every day. But our business is changing. A number of different challenges in our business. We see things happening globally in terms of energy. You saw the terrible tragedy in Japan and the effects of that, and the questions about nuclear power, and that's affecting already the global fuel markets. We've seen prices changing in the gas and coal markets around the world. We are facing aging infrastructure in our business. A lot of our facilities around the state and around the nation are reaching 3 and 4 decades of service and will ultimately have to be replaced with new technology. We're seeing an increasing number of questions related to environmental regulations. As a country, we want to continue to make improvements in our air and water quality. And we see new energy policies being contemplated, whether it be for clean energy, renewable technology, new nuclear, those sorts of things are continuing to be debated at both the state and the federal level. You know, one of the things that we're doing to get ready for the future, we are in the middle of a merger with Duke Energy in North Carolina. And when we complete this merger at the end of this year, we will be the largest electric utility company in the United States. You know, and with that comes responsibility. And one of the things that we intend to continue is our commitment to deliver clean, affordable, and reliable energy to our customers. We will be doing that after the merger is completed in 7 different states for over 7 million customers in those different jurisdictions. And I know that point is important to you about clean and sustainable, because I know that's something that's been an emphasis. We heard the remarks already this morning about the emphasis that you all place on that, not only in the projects today, but in the campus in general, and that is something to be very proud of. When we think about the energy future at Progress Energy, we think in terms of a balanced solution. No one answer is going to provide for our energy future. We think of 3 things primarily. Energy efficiency. It makes no sense for us to waste the resources that we have. We want to make sure that we are providing the power for our customers' needs, but we also want to make sure that we're working with them in partnership, that we're using that product efficiently. Renewable energy, alternative and renewable energy, and we're starting to see encouraging signs where some of the costs for some of the alternative energy is moving more towards appropriate market costs, and we're starting to see more implementation of things like solar, especially here in the state of Florida. and then state-of-the-art power systems. So I want to mention a little bit about each of those and what we're doing at Progress Energy. You know, we have about 180 megawatts of renewable energy under contract today. The way the system works in Florida, we don't produce a lot of that ourselves, but we purchase it and use it as part of our energy supply here in Florida. And we have up to about 500 megawatts of additional that is going to offer the potential for new energy supply, solar in particular, that folks are looking at for development around the state as well. You know, we just recently received approval from the Public Service Commission for an expanded version of our solar program, which we call SunSense. And we had an application period open for photovoltaic credits for both residential and small commercial. And I'll tell you, the monies that were allocated to that were sold out in 48 hours. And that program is fully subscribed, and we're looking forward to the implementation for a number of different locations, both in individuals' homes and businesses around the state of Florida. We also work with schools around our system to install 10 kV solar arrays in high schools as an example, and work with the curriculum there to make sure that the learnings from the PV systems are incorporated into the science curriculum for the students as well, to hopefully inspire new and creative ideas around that as well. And on solar water heating, one of the most economical ways to use solar, in particular in the state of Florida, is water heating. You know, one of the challenges with renewables is that source is not always there. So if you have the ability to store that energy, as you would do in a thermal application like solar hot water heating, we offer a $550 credit for a new installation for solar water in people's individual homes. You know, electric vehicles is another area that I think is up and coming and shows great promise. This is an area that we are very involved in. And you hear conversations by the policymakers about energy independence and our dependence on foreign oil. And sometimes I think that gets translated inappropriately to the energy supply business. But yet in the electric utility business in the United States, less than 1% of the power generation today comes from oil. You know, oil is really a transportation issue. If you think about that, it's really automobiles and trucks and those sorts of things that use the majority of the oil that we consume here in the United States. So this is where electric vehicles offer some great promise. And we're involved on a number of fronts. We're involved with research and development at a number of universities, including UCF. We have partnerships with a number of the major automobile manufacturers, folks like Ford, Nissan, and GM. We have a couple of projects with local government that we call Project Get Ready. We have one here in Orange County as well as Pinellas County over near St. Petersburg, where we are contemplating with the local governments how to build the infrastructure so that people have the capability to do charging if they are out and about and away from their primary residence. We are testing electric vehicles in our fleet. As you can imagine, a company like ours has a lot of fleet vehicles, both for our employees that are out and about working throughout the day, and a number of our trucks that you see out on the road. So we're experimenting with that, and we have a fairly significant research project underway in North Carolina with NC State University on battery technology for electric vehicles. So you think about the continuing concern for carbon and the talk about carbon regulation at the federal level. You know, 80% of the carbon that goes in the environment today comes from two sources primarily: transportation and power generation, fossil fuels, primarily coal and natural gas. So the technology exists today. Obviously there's a question about the cost of that technology, but the technology actually exists today to take care of that 80% of the carbon. Nuclear, which is carbon-free in terms of its emissions, and electric vehicles charged at night by nuclear. If we wanted to pursue that as an environmental and an energy policy, that technology does exist. So that's available, and we're interested in trying to pursue advancing these technologies. I think, you know, the automobile fleet in the United States does not turn over very quickly, and there's still some economic challenges with electric vehicles, but we're starting to see more widespread adoption, and we're trying to prepare for that future. The other area of our focus in terms of state-of-the-art power systems is what you hear a lot about, is called smart grid. And smart grid means a lot of different things to a lot of different people. We were one of the recipients of the $200 million grant from the federal government, some stimulus money, to advance smart grid. We will match that with about $400 million of our own money to try to move new technology. For us here in Florida, our focus is really in 3 individual areas. One is direct load control. We have over 500,000 individual devices in people's homes around our system that allow us to reduce peak demand during the hot summer days and the cold winter mornings. We essentially have a communication network that allows us to reduce the demand by turning off and on appliances in people's homes, primarily water heating, pool pumps, and heating and air conditioning systems. And in exchange for that, those customers that participate get a credit on their bill every month. So that allows us to reduce demand about 1,000 megawatts, which is the equivalent of 2 large gas-fired power plants that we would have to otherwise build to serve that peak demand. The other focus is smart metering. We will install approximately 80,000 smart meters in small commercial businesses and allow those businesses to have more real-time information and to apply that information in a way that hopefully will help them become more energy efficient in their business. And then we're doing a lot of work also in our network. You know, the smart grid primarily for us is from the generating source to an individual's home or business. And the more intelligence that we put in our grid system, the more efficiently it's going to operate in terms of its losses, in terms of predictive maintenance, and in terms of recognizing problems on our system where there are outages and allow us to restore that power more quickly. So those are the primary areas for smart grid. A lot of other folks talk about smart grid in the home. And I personally think that's going to lag a little bit. I think there are a lot of things going on in terms of new technology and smart appliances that as people cycle appliances will have more intelligence in the home that will allow people without a lot of effort to basically make sure that they're consuming power in an efficient way and during times of the day when it makes the most sense. But really today I want to focus on you and what you're really doing as the students and the leaders in the future on how we're going to secure an energy future. You know, when our company was formed a little over 100 years ago, Ford had just introduced the Model T, and we operated electric streetcars, which had just replaced mule-drawn trolleys. And now, a century later, we're talking about things like electric transportation and other emerging technologies. So the work that you are doing here today can help our industry in terms of our long-term transformation of how we produce and use energy in this country in the future. And that's a pretty exciting proposition. You know, the energy future is literally in your hands and in some of the amazing projects that I'll have an opportunity to see here this morning. So as you continue your studies here at the university and prepare for graduation and life and work beyond college, I challenge you to continue to think big, reach high, and push the limits in the search of new technological advancements and the next big breakthrough. So congratulations on all the great work that you are doing. I'm anxious to see the projects after my remarks, and thank you very much for allowing Progress Energy to be a partner again in this year's symposium. Thank you.
Thank you very much, Vinny, for your very insightful remarks. And thank you, Progress Energy, for your support and continued support of our College of Engineering and Computer Science. We just hope that our partnership and collaboration will continue for many, many years to come. Before we start the program, I want to take an opportunity to thank Mr. Bob Rich, our Director of Corporate Relations, for organizing this symposium. There's a lot of hard work behind the scenes. He and his staff have put in just an outstanding program that I'm sure you'll enjoy as we move on to the presentations that will be coming from the students. So again, thank you all for participating in this what I think is a terrific event. Enjoy the symposium, and best wishes to all the students as we start the official program of presentation.
Good morning. My name is Bob Rich, and I'm pleased to be here today and to be able to start the symposium off with some exciting presentations. what was not intended, but certainly what we've done. And I think Mr. Dolan will find today that many of the things that we are doing mirror exactly those strategies that he outlined. And from home energy management to solar to electric cars to all these things that we're in the middle of. We didn't plan it that way, but those are the projects that you personally chose and have done so well on. So again, thank you for your efforts so much, and also the faculty advisors for all their leadership that they've provided. Also, I'd like to thank ASHRAE Sawyer, who's a graduate student who's working with us on this symposium and some other projects, and Siobhan Binder, who's in Dr. Riley's office, who's been very helpful in terms of getting everything organized. So we thank both of you, and as you know, you've all got to know ASHRAE, so we really appreciate her efforts. To start off today, we will talk about something that's very relevant to all of us, and that's parking at UCF. And we have an electrical engineering computer science team that's come up with an innovative session regarding parking garage management. I think the challenges we have all here is parking and where we're going to park and how much parking is available at any one time. This team addressed that and will be providing some insight and hopefully some innovation for the university that we can continue on. Secondly, we'll have the home management system in this session. And I also would like to ask the teams of the low concentration thin films with solar tracking to come to and get set for your presentations, as well as the solar Stirling engine team, the solar powered tracking team, and the electric vehicle economy mode control team. So if you would also come over here to be ready to get up for the next presentations, that would be great. So we'll start out with our parking garage management system. Gentlemen, it's a pleasure to have you. Thank you very much.
Thank you. All right. Good morning. Thank you again for coming. My name is Kevin Firestone, and let me just begin by saying we are very grateful and thankful for the opportunity to be on this stage and lead off the senior design groups with our presentation. Our presentation is the parking garage management service. No one enjoys finding parking on campus, especially when the garages are nearly full. Circling the garage for 15-20 minutes trying to find a space is very stressful. Oftentimes, students will park illegally just to make it to class on time or make it to a test. What this usually results in is this bright green ticket you see here that everyone knows and loves, right? The more adventurous students, especially under stress, will do what's in the image on the right. UCF is the second largest university in the country. It has over 56,000 students and 7,000 faculty. Last year, 45,000 parking decals were sold on campus. This does not include daily permits, temporary parking, or event parking. However, there's only 22,800 parking spaces available on campus. This is spread out among various flat lots and 7 parking garages. Each garage holds 1,300 vehicles, and each space in that garage turns over about an average of 3 times a day. This means there's between 3,000 and 5,000 vehicles passing through each garage and 20,000 vehicles through all the garages each day. This high turnover means a lot of parking tickets as well. Last year alone, 48,000 parking tickets were issued on the campus. At an average cost of $20 to $25 per ticket, this means over $1 million in fees. So our solution was to design a system that would quickly and easily identify spaces for drivers who want to find parking. What we chose to use is a wireless IR cameras mounted throughout 1/4 of a garage that are detecting about 10 spaces each to determine whether or not a space is occupied or vacant. From there, our images are sent to our laptop computer. A computer vision algorithm will then process that image and determine a count of open and occupied spaces. The open spaces will be displayed on a variable message display throughout campus and the garage. This way, drivers, as they're coming to campus, know where to go to find parking quickly. Also, this can be updated to a website. The website will allow students to check garage capacity before they ever leave their home or on their smartphones with a possible expansion to a smartphone app. To power our whole system, we're using a 235-watt solar panel that will be mounted on the side of the garage. It feeds into a 12-volt battery and charge controller and inverter. Our inverter we built ourselves. It is centered around a microcontroller to drive both our modified sine wave and our battery meter. Our battery, which once it drops below 9 volts, will just turn off our inverter and trigger an automatic transfer switch, which will enable grid connectivity in case of emergencies. This will allow our battery to recharge so as not to damage it. Once it's recharged, our system will then be self-sufficient. Okay, Steve?
Thank you, Kevin. Hello, my name is Brian Clark, and here we're presenting the camera layout for our project. As you can see in the garage layout below, there are green shaded regions. These shaded regions indicate the area of view that a camera will have. Where the shaded regions come to a point is a position of the camera within the garage. These points were chosen in order to allow for the maximum amount of parking spaces to be covered while also maintaining a high level of accuracy for vehicle detection. Also demonstrated within the garage layout are the red indicators. These red indicators are the positions for the programmable display board. As Kevin mentioned earlier, these display boards provide information to incoming drivers as to where in the garage there are available spaces. Now, these display boards will be a huge improvement to the existing signs located outside of the garages currently. As many of you may know, these signs only indicate whether the garage is full or closed. I'm sure many of you don't even bother to look at it anymore as well. I sure don't. When I drive in, I just hope for an open space to be available as soon as possible so I can make it to my class on time. Above the garage layout are images from the actual camera's view. In the top right-hand corner, you should be able to see that there are two vehicles trying to locate an empty space. Many times in this situation, they find themselves, because they do not have the information provided to them from the programmable display board where available spaces are, they end up circling around constantly around the garage numerous times while also wasting gas. So because of this circling, I like to refer to the garage as a shark tank. The vehicles are constantly circling around, hunting down that available spot. Many times, they'll take the bait of a person walking within the garage, hopefully thinking that they'll be leaving the vehicle. Sometimes they're not even leaving, they're just checking their car for something that they forgot, and then you have to start all over again. So, this video demonstration shows the vehicle detection for our project. The vehicle motion will enter the camera's view, and the detection will identify that vehicle. So what happens is a vehicle will enter the camera's view. The detection will pick up that vehicle and identify it. When it pulls into a position and comes to a complete stop, the detection will complete, and then that space will be indicated as taken. The detection is limited to only vehicles, so any other objects moving in its view in motion will not be detected. So if a person's leaving their car, they will not be picked up as an object in motion and positively identified as a vehicle being parked in this position.
All right, thanks, Brian. All right, so I'm Stephen Harrison. I'll be presenting the existing financial issues with today's parking system. As we previously mentioned, there are over 56,000 students at UCF, and over 45,000 parking decals were sold this past year. The average student will travel to campus around 64 times, which is 2 classes a semester, meeting twice a week. So each time a student has to come to campus, it's going to cost them money. For every 5 minutes a car is idling, it's going to waste 1/8 of a gallon of gas. So with 45,000 drivers, this is going to come out to wasting 162,000 gallons of gas, costing about $500,000. Since gas is exceeding $3.50 a gallon, it'll probably just be cheaper to hire a freshman to stay in the spot so no one else takes it from you. But keep in mind that this is only 5 minutes of idling. This doesn't include driving around for 10, 20 minutes trying to find a spot, which driving will consume gas a lot faster than idling will. So this is a graph we created to show the financial burden parking is putting on UCF students and faculty. Like I said before, idling at 5 minutes is going to cost about $500,000, and if you double that, idling at 10 minutes, it's going to be over $1 million every year. And we've all been in situations where we come to campus an hour early for a test or a presentation we have that day, and parking takes so long that we end up running to class 5 minutes before it starts. This problem leads students to park illegally, resulting in an additional $1 million every year. So if we add up the best 2 possible scenarios out of this, every year, close to $1.5 million of student money is being thrown away, with it reaching up to $2.2 million, and possibly even more than that if it takes you longer to find a spot.
Thank you, Stephen. My name is Eric Tryon.
Today, I'm going over the goals of the project. The goal is to diminish the amount of gas that is wasted per semester, because about 160,000 gallons of gas is wasted per year, and that's just finding a spot. Now, we want to reduce the amount of parking tickets because right now there's about one parking ticket written per student per year. According to a recent teachers poll, teachers love our project because students no longer have the liberty of using an excuse of finding a parking spot for being late for classes or tests. We are also fighting for carbon neutral here at UCF, and we implemented a solar panel. Therefore, we're fighting against the carbon, trying to become carbon neutral by the year 2050. Now, we want it to be expandable for a whole garage and not just a quarter of a floor. Also, there's security. This wasn't an initial goal for us, but a couple weeks ago while testing inside the garage, UCF PD came up to us because apparently it looks suspicious when you're trying to survey every car in the garage. Well, after a little conversation with them, they decided that we actually have something for an application in security for detecting people who break into cars on campus. Now, on behalf of our group, I would like to thank all of you for coming here today, and a special thanks to Progress Energy and Dr. Ritchie for all their help and support.
All right, my name is Ryan Jones. I'm an electrical engineering major. I'm here with Zineb Peter, another electrical engineering major, and Denny Kilgore, computer engineer. And we'd like to present to you the home energy management system. We are sponsored by Progress Energy, and we're advised by Dr. Ritchie. So one of the major problems we are trying to tackle with our project is the fact that power bills really only give you a look at the overall usage in your house. You don't get an itemized list of what's using more power than you think. The other major problem we're trying to tackle is standby power. And this is caused when you turn off an electrical device, but it's still drawing power, which happens with your home theater system, a laptop when you just close the lid, and even your cell phone chargers. When you leave it plugged in and your cell phone isn't charging, it's still drawing power. Some research we found, which came from 2006, showed that standby power can contribute up to 10% of your home power bill per month, which is no small number. On top of that, how much time are you really using your house that you need everything to be powered? It amounts to almost 50% of your week. Half of that time you're going to be at work, the other half you're supposed to be sleeping. So what if you could program your house to shut down when you didn't need to be using it? And what all this amounts to is that per month in the entire United States, consumers use almost 72 billion kilowatt hours. And that means that $800 million is wasted by consumers per month due to standby power.
The product we came up with basically consists of two subsystems. The first one will be measuring the power being consumed by appliances plugged into it and sends the data wirelessly to a control unit, touchscreen. The second subsystem will allow the user to turn on and off appliances per their preference. But more importantly, what our product will do is will allow you, the consumer, to be in charge. It will allow you to change your power consumption habit by giving you a visual incentive.
My name is Dennis Kilgore, computer engineering major, and I'm going to tell you how you're going to use the thing. Basically, all you have to worry about is where you're going to put the touch screen in your home. You're going to be able to plug all your electronics into the outlet that we provide. Data of the power usage of those appliances will be transferred to the touch screen, where you'll be able to monitor all the metrics. That'll include power usage per module, the dollar amount of that power usage. You'll be able to turn off and on all the modules individually or all at once. And all the data will appear in real time. We're measuring over every second. It's going to return a value of your power used. We have right now 3 modules in our project. Here you can see that we have some of them turned on and off into random values. And there's a master control button there. an options button, and budget remaining. We would like to thank Dr. Ritchie for advising us on the project, Progress Energy for giving us funding, Bob Rich, and everyone in the Electrical Engineering and Computer Science College. Thank you.
Hello, good morning. My name is Sean Murphy, and I will be graduating this spring semester with a bachelor's degree in computer engineering. And we are here to present to you today our project, Low Concentration Thin Films with Solar Tracking, and with my partners, Amanda Klein, Jesse Trawick, and Motier Bullion. So you may be asking, what is low concentration thin film with solar tracking? Well, our design is a tracker that seeks the most optimal light setting for maximum efficiency. We will be having 2 solar panels, one that will be facing towards the sun during the tracking time, and the other will be facing down towards a reflective dish so as to capture any light that escapes from the first panel. The outcomes and benefits of our project include an alternative to roof-mounted panels for people who live in apartments, lease homes, or who want clean, portable power. So our design will be a portable, on a cart, will be easy to install, or it won't require any installation, and will be easy to move around. So another benefit will be eliminating installation, mounting, and labor expenses. We are also increasing the efficiency of thin film solar panels using solar tracking and optical manipulation. And a final benefit is we will be including a consumer power monitoring interface that will allow the consumer to see how the output of the system is while they're using it. There was a choice between crystalline silicon and thin film solar panels, and nowadays crystalline silicon is a typical type that consumers buy. However, it has been shown that by 2012, thin film production capacity is greatly increasing, and at the same time, the market sales for thin films by 2015 will increase by 16%.
Hi, my name is Amanda Klein. I'll be graduating this spring with my bachelor's in electrical engineering. And the main point of our project was to determine which type of solar panel we wanted to choose between silicon, the crystalline silicon, and the thin film solar panels. Crystalline is what's typically on the market today, and we looked and saw that they're very thick and bulky. They have a lot of extra weight, and we're trying to slimline our design. And also, silicon is a material that has a lot of competition with the electronics market when they make all their ICs for computers and other electronic devices. So the price is still steady price, so the price isn't going down. But the cost per watt so far is at $1, which is not too bad for a thin film panel or for a crystalline panel. So we looked at thin films. Thin films is a very light and flexible material. They don't have to use nearly as much as a crystalline wafer, which keeps the weight down, and you can apply it to any type of surface. Thin films also work well in cloudy and hot climates where crystalline silicon efficiency drops. This is good for Florida because we happen to have temperatures spike over 100 degrees and we get a lot of cloud cover. So this way you can have higher power output even during these conditions. And as of now, we have a record cost per watt of 76 cents per watt, which is drastically increasing throughout the years, which makes thin films a contender for the solar market. This graph shows the main purpose of why we chose thin film. The top dark line is the typical crystalline silicon, and we see that the price per watt is decreasing at a very slow rate to going down to $1 for typical market prices. But thin films has a lot of technology behind it and a lot more research, so they're cutting the price down even quicker using SIGs, which happens to be copper, indium, gallium selenide. These are 4 different components, so not one particular component will add drastic to the price of the material.
Hello, my name is Jesse Trawick, and I'll be graduating with a bachelor's degree in electrical engineering in May of 2011. So because we're designing this project to be used in residential leased homes or apartments, we wanted to make sure that our design was accessible and easy to set up as possible, and also as energy efficient as possible for the size and cost. So we used several innovations to make sure that that happened. The first of which being a portable, fully functional design, meaning there's no installation required. This unit comes completely set up, so you can just set it out in your backyard or your front yard or a porch or wherever you want to set it up, plug it in, and it's good to go. With further refinement on this design, this could actually be deployed in disaster-stricken areas like the recent events in Haiti and Japan as a power hub for volunteer crews while the power grid is down or gas may be scarce for power for gasoline generators. The second feature we added was single-axis tracking. What this does is it turns the panels to the sides to make sure that the panels are always seeking out the most sunlight possible, thus increasing their power output. This is something that roof-mounted panels for residential applications cannot do. So we should see greater power output during the early morning, late afternoon, and during any conditions where there might be cloud cover. And the last feature we added was the reflective solar trowel, which catches light that passes past the first panel and reflects it back onto the panels, with the goal of, again, increasing the power output for a given light setting with the same amount of panels.
Hi, my name is Motiur Bhuyan. I'll be graduating with a bachelor degree in computer engineering this semester. For monitoring purpose, real-time power graph will be accessible via internet at any time of the day from anywhere. The consumer will be able to monitor how much the power they are saving by using our system. By giving consumer this opportunity to access to the system remotely, they will be more interested to the renewable energy, and by sharing their information to their friends, they will widen the market for the renewable energy and also the system and through the word of mouth.
So what does this mean for the future of residential solar? It appears to us that thin films can become a less expensive to mass produce alternative to crystalline panels with emphasis on mass production. Because in 2010, second quarter alone, more than 30,000 apartment homes were built. Just built, not already existing, just built. So this is a growing market that currently does not have access to residential solar because they don't have permission to mount on the roof. By using our portable self-contained modules, we can reach this market, and the effect of this would be large spread. We also believe that solar tracking can reduce the space taken up by panels in a residential home by increasing the power output we gain from a set amount of panels. And interactive power monitoring will allow the consumer to see and feel the effect that renewable energy has in their lives. And when they see it and feel it, they get excited about it. They share that information with their friends, and their friends get excited about it. And when that happens, a wave starts. And we see renewable energy becoming a staple in every home. Special thanks to our sponsors, Progress Energy, and our advisors, Samuel Ritchie, Dr. Weeks, and James Harvey, for assisting us in making this design a reality. And we'd also like to thank Abner from Swiss Components in Melbourne, who helped us with some metalworking we had to do, and Sean Pagliari, who is a Master of Science in Ocean Engineering at FIT, who helped us with some of our mechanical design work.
Good morning. We are the solar-powered Stirling Engine Group.
A brief history of the Stirling engine begins in 1816 when Robert Stirling invented his air engine, later named after him. Its early uses included the water pump, sewing machine, and fans, but it also has other applications such as powering a small radio and larger applications as NASA's use in an automobile in 1970, and also as a heat pump for refrigerators. Recently, it's been used in low-temperature differential engines for the sake of novelty and for minute power generation. But today, it has various applications, such as powering homes. It's also used in submarines and other cooling applications.
So the intention of this project is to design a cost-efficient, renewable energy source. Because as we know, in today's society, the need for energy is increasing daily. The purpose of this project, of this engine, is to promote an alternative form of energy. Well, we have specific goals which we laid out at the beginning of this project, which were to get an efficiency for the engine of at least 20%, to get a temperature difference from the hot cylinder and the cold cylinder of 200 Kelvin, and to reach a max of, or a minimum of at least 500 Kelvin at the top of the hot cylinder.
Okay, so the Stirling engine begins by collecting solar radiation and it focuses that through a Fresnel lens. That Fresnel lens concentrates the heat onto the heating element of the engine. Now, a Stirling engine works by creating a temperature differential within the engine. The engine is made up of a heating element, a cooling element, and the internal components consist of a displacer and a piston. Now, the displacer, its purpose is to separate the hot fluid and the cold fluid and transport them back and forth as necessary. The piston is what seals off the internal components of the engine and creates the pressure needed. That combined with heat input for the engine produces the mechanical work, and from that mechanical work, we are able to produce electricity.
Basically, the theory begins, if you look at the PV diagram on the left-hand side, we have two expansion processes happening, as well as two compression processes. From state 1 to state 2, we have an isothermal expansion. From state 2 to state 3, we have an isochoric or constant volume expansion. From state 3 to state 4, the compression begins, and we have isothermal compression. And the cycle is finalized from state 4 to state 1, in which we have an isochoric or constant volume compression.
In order to better aid the thermodynamic cycle that we're describing in our Stirling engine, we utilize both the geometry in our design and our material selection to give us a better advantage while the engine is in a constant state of running. You can see that the displacer, the upper piston that's going down right now, utilizes the same matching geometry to both prevent any binding in the system and also to help provide a swirling action to better dissipate the heat throughout the working fluid. We incorporate a regenerator inside our displacer to increase the efficiency overall when the working fluid goes past through the center portion to our power piston. Our power piston rides only inside our cold cylinder, which is made out of aluminum, to better dissipate the heat from our heat source, which will dissipate it out, thus continuing the cycle. The power from this power piston will go through a rhombic drive, which consists of several yokes and 4 link arms. These are connected by pins into our gears, which give us the 90-degree phase difference which we need for the Stirling cycle. The energy is transferred into the flywheel from here, and this is how we create our energy. As you can see, what we were trying to do is our engineering style is not designing one part for one purpose, but rather each part completes multiple tasks. And this allows us to have a compact design and still get the required work done.
Thank you.
Hi, my name is Kenyo Martin. And today we're going to present to you our project of SEGs. I have a quick question for you guys before I get started. How many of you own or are familiar with the Nintendo Wii console, by a show of hands? Yeah, with over 40.53 million units sold, there's a huge market of appeal for gaming, and that is the motivation behind our project. What SEG stands for is a solar efficient gaming system. So the primary goal of SEGs will be to power a Nintendo Wii. It will also charge a 12-volt battery, and it will also be used as a solar panel and battery monitoring system.
There are many benefits for our project for the solar panel tracking device, or SEGs as we call it. Mainly the type of focus we're trying to do is toward solar energy. Most of people now today are trying to delve away from the use of fossil fuels and move more toward renewable sources. With our project, we want to have the generation of it be more used. As you can see on the screen to your right, there's a graph showing the amount of generated power in the United States. As you can see, only 1% of energy is used towards solar power in the United States. As we said before, we want to try and generate it more within that boundary. With this project as well, it is, with the use of the solar power, it's more effective, cost efficient, as well as safe and reliable. With it, as Keneal mentioned before, it's going to be powering a Nintendo Wii. as well as a television using an AC to DC converter, as well as going to charge a 12-volt battery. As we can see as well, Florida is one of the biggest known places that uses solar energy as well, and it's a good thing that we're trying to go into this project so that we can show more of the country what we can do with this.
Hello, I am James Lilly. I am an undergraduate in electrical engineering. Here we have our design flowchart. Starting on the left, we have our solar tracking device that gathers photovoltaic energy. This energy is then sent to our DC to DC converter, and that power is also going to be displayed on our monitoring system. The power from the DC to DC converter will be used to charge our battery, and the voltage on that battery will also be displayed on the monitor. From the battery, the power will then be sent to an inverter. This inverter will then in turn be used to power our Nintendo Wii. So on this slide we can see our SEGS prototype. On the left we have our solar tracking system. This system has 90 degrees of vertical rotation and 360 degrees of horizontal rotation. To track the sunlight, we are using 4 photodiodes, 2 for left and right, 2 for up and down. Our microcontroller will use these diodes to sense the sunlight and turn the panels towards the diodes with the highest intensity. Finally, to move the panels, the microcontroller is controlling two motors, a stepper motor and a linear actuator. The power that is produced from the panel is around 20 watts. A Wii has an average power consumption of around 16 watts. That being said, our tracker can produce enough power to independently power the Wii. But in case we don't have a self-powered television, the inverter combined with a 12-volt battery can supply up to 200 watts to power the Wii and the television. While the Wii and the TV are tracking this, the system will continuously charge the battery, extending the Wii playtime until the power is depleted from the load.
Okay, as you can see on the screen right there, there's a prototype of the display that we have used for our SEGS model. As you can see, we have employed the use of the Hitachi HD 44780 LCD display. On the screen in front of you, you can see that one of the components that we're trying to go towards is showing the panel voltage, as well as the battery voltage, and lastly, it's not displayed on there, but we're going to display as well the battery life as well in a percentage. This is mainly going to be the checking hub for the solar efficient gaming system, so that the consumer will be able to check on the progress of the battery as well as if the solar panels are working correctly.
All right, so we'd like to thank you for your attention this morning. We'd also like to thank Dr. Samuel Ritchie for advising us throughout our design, also Progress Energy for funding our project, and the Department of Engineering and Computer Science here at UCF. Thanks.
Good morning, everyone, and thank you for coming. My name is Shantice Diaz, and I'm studying to be an electrical engineer and will be graduating in December 2011 with a minor in mathematics. As a group, we'll be presenting the EVMQ. The EVMQ is short for Electric Vehicle Economy Mode Control Unit. As a student, we are part of the Department of Electrical Engineering and Computer Science. With an advisor, our academic advisor is Dr. Ritchie, Samuel Ritchie, which we would like to thank for being there throughout our academic career. Though we are the main designers of our project, our sponsors consist of 3 companies. Our first company is Power Grid Engineering, which is a company that caters to the design and protection of control systems for utilities. They provide the initial design and also are responsible for leading us to our next sponsor, which is Tech to America. Tech to America is a company who does roofing and also does solar panel installations. They provided the fully electric 2006 Ford Ranger truck. Last but not least is Progress Energy. They provided complete financial support, which made our idea come true. So what is our project? The EVMQ is a control module that contains several microcontrollers that will implement an economy mode for our electric vehicle. This module contains several microcontrollers and will be connected in series with the picture on the top left-hand corner, and this will calculate optimum acceleration. And it will calculate this optimum acceleration by taking in several inputs such as RPM, speed, current, and acceleration.
Good morning, everyone. My name is Vanessa Baltajolu, and I'm studying electrical engineering here at UCF. I'm graduating August 2011. Today I'm going to show you an overall diagram of our project. This is our 12-volt auxiliary battery, and this is the input from the user, which is in the form of a foot pressing down on the gas pedal. Both of these inputs feed into the potentiometer. Now, normally a potentiometer sends a direct signal to the motor controller. However, our module is connected in series between them so that it can replace the potentiometer signal with its own optimized output signal. To produce this output, our control unit takes in readings from the potentiometer and other sensors around the vehicle. The control unit is made up of a series of microcontrollers that each serve different purposes. These microcontrollers allow for data storage, safety precautions, and the calculation of optimum current. The output from the control unit is a voltage that is representative of that current, and it's fed into the motor controller. This can be viewed as a variable dimmer switch that controls the flow of current to the motor. This is our electric motor, and here you can see our 144-volt battery pack consisting of 12 12-volt batteries. Now, there are several specifications that were set between our group and our sponsors. We intend to increase the vehicle range by 5 to 10%. We want to allow for up to 90 minutes of data recording, even though the vehicle can only drive for up to 45 minutes on a single charge. And we are using safety features such as individual microcontrollers and runaway acceleration prevention. There will also be a dash-mounted control switch, and the vehicle is powered by a 144-volt battery pack with one 12-volt battery powering the control unit.
My name is Christopher Chadman, and I'm also a double E major. We'll be graduating this May. I'm going to talk to you about some of the physics going on with our project. The main concept of our project is to minimize the power consumption by limiting excessive acceleration. Simply put, our project works as an acceleration governor. Although electric motors are highly efficient, there's still some power loss through heat due to electrical resistance. R² calculations show that the more current we have going through our system, the more heat loss we'll have. What we've done is constructed an equation, taking the resistive forces on a vehicle, such as aerodynamics, acceleration, and frictional forces due to the tires, related them to power, and this way we can come up with an equation to calculate the power needed to propel the vehicle at a constant velocity. The graph below the equation there shows the minimum power needed, or the minimum current required at different speeds. Although this is a theoretical curve, what we'll do is once our testing phase begins with our project, we'll compare our test results with our theoretical results, and from there we'll be able to deduce our heat loss. Okay, another factor to consider is the minimum accelerations needed for different velocities. Low speeds, high acceleration is usually required, whereas higher speeds, lower acceleration is more acceptable. For instance, going from 5 to 10 miles an hour in 5 seconds is kind of impractical, whereas from 45 to 50 miles an hour is a little more acceptable. So this is a second factor that will be taken into consideration when calculating the optimum acceleration for the vehicle. The graph here is a logarithmic function we created solely for demonstrational purposes to show different accelerations at different speeds, or minimum accelerations at different speeds. Okay, we've also considered some future applications that are possible for this project. Since there are many modifications and converted EVs, each module will have to consider different variables for each vehicle. This can be accomplished by custom designing each module or creating a way for the user to change settings according to their needs. A more advanced version of this project could also be used in hybrid vehicles. Its obvious potential for a data recorder can also prove to be invaluable for anybody wanting to record test results for modifications to the vehicle or calculate mileage and performance. I'd like to thank Dr. Ritchie and Dr. Weeks for their support, and also Progress Energy for putting this all together. If anybody has any questions, please come see us by our booth. Thanks.
It's my pleasure to introduce Carlos Velez. Carlos is an undergraduate major in mechanical engineering and who participated in the senior design in our first year. And because of his involvement and expertise, he was approached by a corporate sponsor for some additional research. And this research, I think that you all will find very enlightening and also very close to home, because it's going to be dealing with the finding and detection of oil leakage in abandoned oil wells in the Gulf of Mexico. And since the economic impact this has on Florida as well as the world, so this has a great deal of possibility for us, and obviously Carlos will be able to hopefully take that to the teams to the next step forward. Carlos, thank you.
Good morning, everyone. My name is Carlos Velez. I'm a graduate student here. I remember exactly a year ago I was presenting my own senior design project here when I met some Harris representatives and we started talking about some wave energy research we were doing at the time. This led to further funding where Harris agreed to support 4 senior design teams in a collaborative effort for a multidisciplinary project that has some very environmental good components to it. Okay, so what's the problem statement? Currently in the Gulf of Mexico, we've been drilling for ages. Since the 1940s, we've been constructing oil wells to try to extract oil from the Gulf, and almost half of these are abandoned. So you have 27,000 currently abandoned oil wells in the Gulf of Mexico. They're in very high pressure regions, very corrosive environment, very prone to break, and no one is monitoring them. Currently, oil could be spilling from them. We wouldn't know any difference. So what we'd propose is a system that can monitor the abandoned oil well, detect any oil leakage, and prevent any oil disasters. So Harris kind of nicknamed this project the AWES system, the Abandoned Well Environmental Sensing System. And essentially, we have here an automated sensor system which you attach to a pre-existing abandoned oil well. It'll detect any oil leak, send the signal back to your surface buoy, which will post-process the data and send a wireless signal back to your headquarters saying what oil well was broken and how to repair it and when it can get fixed. Now the buoy has 2 functions. It not only communicates to headquarters and analyzes the data, but it supplies energy for the sensor system at the ocean floor. And it supplies energy by harvesting the local wave energy in the area, converting it to electricity, and supporting the sensor system. So it's fully automated, it's clean, and it's environmentally friendly. So to break up this project, we took 4 teams, 3 from the mechanical department and 1 from the electrical. One is a sensor team, which will design the automated sensor system for your abandoned oil well. Their goal is to detect any oil leak and report it. Second is a turbine team, which will convert the motion of the buoy into a rotational motion to drive a generator and create the electricity needed for the sensor system. Thirdly, a buoy team, which will enclose all of the electrical components, the turbine, and really be the driving force for the turbine. And lastly, our electrical team, which conditions the electricity created by the generator, stores it, and supplies it for sensors for use for the sensor system. I'd like to thank the Harris Corporation for their great help and advisement and funding for our project, and Progress Energy Showcase for having this event and for allowing us to meet companies and do more work with them, and the University of Central Florida and the MMAE and EACS department. Without further ado, I'd like to introduce the first team, which is the sensor team, and come up. Yep. Thank you.
Thank you, Carlos. My name is Joe Torciano. I'm a mechanical engineering senior here at UCF, and today we're going to present our senior design project, which is an abandoned oil well monitoring system. Before we could develop our design, we had to learn about the facts of offshore oil drilling. What we found out was pretty amazing. Over 50,000 oil wells have been drilled in the Gulf of Mexico since the late 1930s. Of these, more than 27,000 have been permanently abandoned. We also found out through further research that abandoned oil wells on land can develop leaks over time. And this led to the fundamental question of our project. If abandoned wells on land leak over time, then do they leak underwater? Most importantly, though, we found out that offshore abandoned oil wells are not currently checked for leaks by government or industry. The situation became really apparent when we looked at this map here of the Gulf of Mexico. All the colored dots represent active oil wells as of early 2010. The different colors represent the different depths of the wells, with the shallowest wells being in yellow along the coastline and the deepest wells being offshore in purple. It was at this point that we knew that an oil monitoring system was necessary.
Ruben Osorio, mechanical engineer. I'm here to talk about the main goals. So in our project, we have three main goals. First, we need to detect the presence of oil in water. This is being done by our sensor package that we're going to use. Second is minimal power consumption. This is we need to process the data, acquire the data, and send it back. That leads to our third goal, which is send back the warning signal wirelessly to the headquarters, that in order to inform the company or the government that it's a leakage, oil leakage.
Okay, so my name is Tim Murphy. I'm a mechanical engineering major, and our plan to detect the oil well is to place that funnel-shaped design over there on top of an abandoned oil well. And as you can see, abandoned oil well, they're not abandoned like they are on land. When they abandon them, they put a cap on them, and they have cement plugs. When they abandon them in the ocean, they just place cement plugs on them. So what we plan on doing is placing that funnel on top of the abandoned oil well, so whenever it does leak, we capture any kind of oil leak to go straight through that funnel, and then it'll go into the sensor section where it can be detected. Once it's detected, the fluorometer, which is one of our sensors, will send a signal to the electronics package inside the electronics enclosure. That'll send a signal to the buoy up top. That'll send a signal wirelessly that says we have an oil leak. The fluorometer, which is the heart and soul of our project, detects oil through a unique atomic phenomenon known as fluorescence. The fluorometer emits ultraviolet radiation that we can't see, but if it hits an oil compound, what will happen is the oil emits light back that's in the visible light region, and the intensity of that light is detected by a photodiode in the fluorometer that will, whenever the photodiode detects the intensity of the light signal, it gives off a voltage. The more voltage, the greater the oil leak.
My name's Nick Martin. I'm a mechanical engineering major. As Carlos mentioned earlier, our project is one part of a 14 project proposed to us by Harris, and one of the main goals of the overall project is to use renewable ocean energy to power our sensor package. And there's potentially 800 gigawatts of power that could be had through renewable ocean energy. And this ocean energy is completely clean with no carbon footprint. This concludes our presentation, but before we do, we'd like to thank Harris Corporation for funding and proposing this project, Progress Energy for funding and having us here today, the entire UCF MMAE department, and finally our advisors, Carlos Velez, Stephen Helkin, and Dr. Yoonjun Zhu. Up next, we have the Bidirectional turbine team, and they're going to present their project. Thank you.
Good morning, everybody. My name is Ed Morales. I'm an aerospace engineering major, graduating this semester.
I'm Chris Turner, aerospace engineer, graduating this semester.
I'm Jonathan Donnelly, mechanical engineer, and I'm graduating in December.
I'm Arwen Babas. I'm an aerospace major, graduating this semester as well.
My name's Adam Perdue. I'm an aerospace engineering major, graduating this May. We are the bidirectional turbine team. What is a bidirectional turbine? This is a shot of our turbine. We have a duct through which the water is going to flow. We have blades in the middle, and we have guide vanes on either side. The way that this turbine is going to work is it's going to be rigidly attached to a buoy. The buoy at the surface of the ocean is going to be rising and falling, and as the buoy rises and falls, water is going to be pushed through the turbine in two different directions. The unique thing about this turbine is that no matter if the buoy and turbine are moving up with the wave or down with the wave, the turbine blades or the rotor will be spinning only in one direction.
There are two main goals and purposes for this particular project. The first one is to generate clean energy using renewable, and our renewable choice is wave. So basically our system will be harnessing the energy from the wave, converting it to rotational motion, then producing sustainable power to avoid this kind of disasters right here. The second main goal purpose, the generated power will be stored and then fed to the oil sensor that was introduced earlier to avoid the BP oils. And there's also a great deal of need for this market because there's an attitude in the Environmental Protective Agency to mandate the oil companies for monitoring abandoned wells.
This is the basic design of our turbine. Inside of our case, we have two fixed guide vanes that redirect the flow of the incoming water, and we have blades in the middle, and the blades and the shaft are the only parts of the assembly that move. On the right-hand side, there's an animation showing how whether the fluid is coming in from the top or from the bottom, the guide vanes will continue moving in the same direction.
So our main goal is to integrate the turbine with the sensor and the buoy to have a fully functioning system. But what we've provided you here is a cost and performance analysis of the turbine alone. So when we initially started this project, our goal of efficiency was 30%. And this might initially seem low, so we'll compare it to other power producing devices. First is your car. Cars, gasoline engines are typically 35% efficient, while the best on the market from, say, Siemens is about 61%. So the efficiency of our turbine at this point is roughly 21%. This is not our goal, so there's a lot of optimization left to do. Optimization will generally be done through the geometry of the system, including the shell and the geometry of the blades. If we assume a 30% efficiency, we would expect about 100 watts of peak power and an average of 30 watts. And if this was the case, and we paid $11,000 for our turbine, we would make about $24,000 a year and pay it off in about 6 months.
In this slide, we show that by means of numerical analysis, we actually calculated all the needed parameters for us to meet the power requirements. It was calculated that we needed at least just over 2 meters per second of overall velocity inlet of the water to hit the turbine in order for us to meet our power requirement of 100 watts. So you can see we hooked up our turbine to this water column, and essentially it would dunk the turbine into the tank, simulating the wave movement of the ocean. You can see on the top very, very slightly the overall shaft is rotating in the same direction, whether the motion is going up or down, which is the proof of concept for this project.
We would like to thank our sponsors and contributors, as well as our faculty advisors. We would especially like to thank Dr. Marcel Ely, also Dr. Scott Martin, and Carlos Velez, the UCF graduate student who introduced all of our teams. We'd also like to thank our sponsor, Harris Corporation, and we'd also like to thank Progress Energy for their additional funding. Thank you very much. Next up will be the buoy team. This is the buoy that will be attached to our turbine. So thank you very much.
Thanks.
Hello, my name is Matthew Penn. I'm an aerospace engineer, and I graduate this May. We are the buoy for ocean wave power generation team. So according to the sensor and turbine team, we know that there is a dire need for some kind of system that will be monitoring these abandoned oil wells in the Gulf. But why wave power? Ocean waves pose a greater energy as compared to wind energy. In addition to this, the location and direction of waves can be easier identified than the wind direction. And on top of this, the majority of Earth is covered in water. So this makes virtually any location on the planet able to utilize this new technology. Now, how does it work? This is, the black is a buoy turbine configuration with the buoy on top and the turbine on the bottom. The blue line signifies the water and the waves. And this shows the buoy in the beginning of the wave going up. On top, the buoy's in water that's moving, and down deep in the water, the turbine is very still water. So the only way for water to move through the turbine is if the buoy were to be very buoyant. So on the way up, the water is forced downwards through the turbine, spinning the shaft, and thus generating power. As you can see, the entrance is a converging nozzle, which will speed up the flow of the water, getting a maximum velocity through the turbine channel. This here shows the buoy at the top of the wave, and this here is very similar to the first image. However, this one's moving down and forcing water up through the turbine as opposed to down through the turbine. And now Dan will take it away with the design of the buoy.
Good morning, everybody. My name is Daniel Bell, and I'm a mechanical engineering major, graduating in spring of the semester. Now that we understand how we're going to harness the energy of the waves, now let's take a look at how we're going to accomplish this. The main asset in our system is the buoy. The buoy is going to be is going to stabilize the system and also is going to drive the turbine. The way we designed our buoy is the outer taper is going to have a 60-degree angle, and the inside taper is going to have a 30-degree angle. The reason why we chose the 60-degree angle is because we wanted to have a sudden increase in the volume to increase the buoyancy. Also connected to the buoy is going to be our generator housing. The generator housing is watertight to prevent water from entering and having any contact with the generator. The third system in our design is a hollow shaft that's going to encompass the turbine shaft. Now there's three purposes for this outer hollow shaft. First, it's going to secure the turbine channel and the turbine shaft to the buoy itself. Also, it's going to serve as a watertight seal also for the generator housing. We want to prevent any water from entering that housing and have any contact with the generator. And third, it's going to separate the turbine shaft from all of the forces from the ocean itself. We don't want to hinder any type of rotation for this shaft. The last system in our design is a swivel system. This system was designed to maintain a vertical position of the turbine channel even when the buoy is subjected to the waves that may tilt or rotate it. And to optimize our buoy shape, we use a simulation program called S-Physics, which stands for Smooth Particle Hydrodynamics, which is a computational fluid dynamics program, or a CFD. With this program, we're able to select any particle within the model, and from this particle we can measure a graph of the water velocity through the turbine channel itself and compare it with our experimental analysis, and we can measure or graph the buoy position versus the time that's subjected to it. We have four different experiments that we have conducted. The first experiment was what we did. We did a deflection test on the outer shaft, and Boram here will go ahead and talk about that.
This shaft experiment was tested to determine if horizontal forces will deform the shaft and interfere with the turbine shaft. And the reason we were testing this was in case the shaft deflection or deformation is too large, we will lose the power or energy, which is from the turbine blade and shaft. But as the result says here, the data says the deformation is not too much. It's about 10⁻⁶ order, and it doesn't affect anything because we experiment about 10 pounds of weights at the end of the shaft, and strain gauge was installed at the another end of the shaft. And the result is explaining that the deflection is not too much. I hope that this deflection doesn't affect until 100 pounds or 500 pounds.
Another experiment we did was on a wave simulation table similar to the turbine team used to test to make sure their blades were spinning. What we plan to do is test the swivel stability to make sure it remains vertical no matter what the tilt angle is of the buoy. This will also make sure the double shaft system is watertight, preventing water from entering the generator housing. The final test we'll be doing is putting the buoy with all its components in one into the UCF pool because of its depth, and generating man-made waves that are consistent and replicable to see how much water velocity we can get through the turbine. And then we're going to compare this data to the turbine group and make sure everything's working properly. We learned a lot during this project. Fluid dynamics, buoy dynamics, computational fluid dynamics, and we had a great time doing it. And we want to say a special thanks to a few people: Dr. Ely, Carlos Velez, the Harris Corporation, Mr. Mark Blue, and from Progress Energy, Asley Soiler, and Bob Rich. Thank you very much.
Good morning, ladies and gentlemen. We are the oil well monitoring system team, the EECS team, fourth and final team for this Harris project. So by now, I'm assuming all of you have a better understanding of what this project consists of. So what I'm going to do is I'm going to give you a brief understanding of what we are bringing to this table. So basically, the idea is to convert or extract the turbine energy that the turbine team will be generating and provide it to the sensors via a generator. So the generator output will be fed into the input circuit, and then that will be converted by signal converters, and we will be doing some processing on that via some software, and finally charge a battery that will provide the steady 12-volt direct current output to the sensors.
Hi, I'm Caleb. I'm going to be graduating this
spring with a bachelor's degree in electrical engineering. I'm going to go over the goals and objectives of this project. Basically, we have to convert the wave energy to the electrical energy by means of a generator. The generator does produce the electrical energy, but it's can't directly be used by the sensors at this point. It's alternating current, and it's going to vary in amplitude. So we need to produce usable energy for the sensors. The circuit itself is going to be exposed to the environments in the Gulf of Mexico, so it needs to be enclosed in a waterproof enclosure. Okay, so the generator signal, as I said before, is alternating current. Because it's coming off of the wave generator, the wave energy is not constant. It's going to increase and decrease, and this signal will increase and decrease as well based on the wave energy. So it's going to be fed into an input circuit. The first thing the input circuit is going to do is rectify the signal. That's a pretty easy process. Once the signal is rectified, it's going to go into a signal converter, and that's going to condition the signal to be a constant 12-volt steady output regardless of the changing amplitude. More than just converting the signal, we also have to implement power management, because what happens is if the wave energy starts to decrease and we keep a constant load on the generator, you run the risk of the generator shaft coming to a standstill. If the generator shaft comes to a standstill, it takes a lot of wave energy to get the generator start back up again. So what our circuit is going to do is charge the battery, but if the wave energy starts to decrease and gets below a certain threshold, it'll stop charging the battery. Now the sensors will still run because they'll still draw current from the battery, and our circuit will wait until the wave energy starts to increase, reaches a level that's sufficient enough to start charging the battery again. And then once the battery is charging, you'll go through this process of the sensors drawing current from the battery being recharged when there's enough waves to do so. So I'm going to turn it over to Lewis to kind of go over the overview of the system.
My name is Lewis Bankson, and I'll be graduating this May with a bachelor's in electrical engineering. Just as a review of the overall system, we have the buoy, which is floating on the ocean top, and beneath that we have the turbine system, so the buoy up top and the turbine. And our electrical components will be housed in a weatherproof containment unit on top of the buoy. So for the end results for this project include an electrical unit built in order to power the sensors, which takes a variable input from the wave energy and converts it to a constant output to the battery. This will need to be suitable for both sea and surface conditions, hence the waterproof containment. The software used in the product will help to make the system more efficient by keeping the output consistent regardless of the fluctuating wave energy. And in the end, the product will be able to produce a steady, constant output to power the sensors. At this time, we'd like to acknowledge and say our thanks to Dr. Ritchie, Dr. Chu, and Carlos, as well as Progress Energy and our sponsor, the Harris Corporation. Thank you.
We are not part of the buoy group. My name is Kyle Flynn. We're the ablative rock nozzle group, and I'll be talking to you about nanoparticles in carbon phenolic. I worked with Jules Cespedes, Charlie Bissett, and Jack Bauer, and we are all aerospace engineers graduating this semester. The purpose of our project is to implement newly researched materials into under challenging conditions to obtain thermal and aerodynamic properties. We're going to be doing this with rock nozzles, and on the left is a picture of a carbon nanotube, and on the right is a picture of a rock nozzle being test fired, and it's a thermal scan.
I'm Jack. So why is a rocket nozzle part of Progress Energy? Basically, it's about the research into the material. We're hoping to get improved thermal and aerodynamic performances out of the material, and that can be applied to the coatings on turbine blades, as you can see there. These turbine blades will use temperatures right now in jet engines say up to 1300 Kelvin. If we can increase that, we can increase the efficiency of the engines and then reducing the fuel cost and fuel consumption, thus making everything more fuel efficient. And groups such as Siemens and Boeing and everybody uses that. As you can see here, carbon fiber chop is on the top and phenolic resin was on the bottom. Those are our two ablative materials, and then we're also using nanoparticles. We're going to use 3 different types of nanoparticles, or rather 2 different with a combination. The first is the Pyrograph 3, which is a carbon nanotube, or nanofiber, and then the second is POS. It was created by the Air Force. Basically, we'll be using a silicon oxide cage, And then the third will be the POS grafted onto the carbon nanofiber.
My name is Jules, and I will be speaking to you about our actual nozzle design. Now, this is where the high-speed part comes from it. The equations you just saw are high-speed aerodynamic equations that we used to calculate such things as thrust, exit velocity. Now, our one requirement was that it would definitely at least reach Mach 1. We definitely wanted this to go supersonic. So as you can see, we've got some design parameters and some engineering characteristics up that show which of our nozzle designs was the most successful and optimal for this project. And to the right of that, we have a rocket motor schematic, and that is the rocket motor that we will be using with its casing. It shows the rocket motor at the top, the propellants down the sides of it, and the nozzle goes at the bottom. What we will be doing for testing of this is flipping that upside down so we don't end up losing our rocket and having to chase it. And we will be thrusting it into the ground, basically, onto a load cell. We'll be testing pressure out of the motor forward closure, and we'll also be using thermocouples along the nozzle to test for temperature and heat flux.
Good morning, my name is Charlie, and the photo on the left is the preparatory of the phenolic resin inside a heated vacuum chamber. This is done to remove all the air pockets and bubbles that may be in the resin. And the photo on the right was us pouring that into the hopper. The photo on the left is the high pressure molding system, the press, and the photo on the right is the press installed in the injection system. The photo on the left is the overall high pressure injection molding system, and the photo on the right is a mock test setup for our testing environment. Testing conditions, as Jules already specified, supersonic exit velocity. We're expecting high pressures and high temperatures of approximately 1,000 psi and up to or greater than 1,500 degrees Celsius. We're going to test the temperature by embedding thermocouples in the nozzle, also on the outside of the rocket motor. We're going to test the pressure by tapping into the forward closure, and we'll have the chamber pressure. The thrust is going to be calculated by the load cell, and the erosion will measure the delta or the difference between the diameters before and after testing.
All right, so our special thanks. We'd like to thank Dr. Go for his advising and the research materials. We'd also like to thank Jeremy Lawrence, Dr. Go's research assistant, for all his help with the construction of the molding press and the general guidance. And then Justin Carl, Dr. Gordon's research assistant, for all the help with the machining and technical advice. And then Progress Energy also for the funding and allowing this to happen. Thank you.
I'd like to introduce Dave Norvell. Dave heads up the UCF's Department of Energy and Sustainability. And as Vinnie Dolan indicated, that this area is a very important area to Progress Energy. It is to UCF in terms of performance contracting and energy saving at the same time. So again, welcome Dave Norvell.
Thanks, Bob. Good morning. I come to you from the Department of Sustainability and Energy Management here on campus, and we are the ones that are operationally responsible for reducing the amount of natural resources that the university consumes on an annual basis. For the third year in a row, I'm proud to come and sponsor a number of projects here today. I think we have a total of 5, 3 that are represented here today in this event. These projects bring real world experiences to the engineering students, and so we think it's an important part of the academic program. In 2007, Dr. Hitt signed the American College and University's President's Climate Commitment, committing the university to achieve climate neutrality at some point in the future, and our department is responsible for coming up with a plan and implementing the plan to reach that achievement. In 2009, we published our first version of the Climate Action Plan for the university. In that plan, we identified 5 key steps that'll bring the campus to the point of neutrality with climate. And we prioritize these steps in order of the quickest payback for the university, the least cost, and the best result. At the top, we've got energy conservation. Secondly, we've got energy efficiency. Thirdly, fuel switching. Fourth, we've got renewable energy production. That's what we're here about today. And finally, we've got carbon mitigation. The projects we are here today to see are in direct support of the American College and University's President Climate Commitment. In the Climate Action Plan, we set a goal to produce 15% of our energy needs by renewables by 2020. This is a very aggressive goal when you realize that we spend nearly $15 million a year in energy here at UCF, or more than $1 million a month. Since this is such a large-scale project, a high-stakes project, we wanted to make sure that we had a multifaceted approach to the design. In fact, nearly all real-world engineering projects involve multidisciplines, and it's important that they work together. And so we thought that was critical to the success of this project. This solar farm project is a perfect example of a systems project requiring a collaborative approach between the multidisciplines of the engineering field. In this project, we involved electrical, mechanical, and industrial engineering. So with that, I want to introduce the first team as the mechanical team coming up. Thank you.
All right, good morning, ladies and gentlemen. I'm Daniel Gould. I'm a mechanical engineering student with a focus on material science, and I'm a member of the mechanical engineering team for the UCF Solar Farm. Our objective was to design and fabricate the mounting system for the photovoltaic array. This is the first year UCF has done a multidisciplinary senior design project, and it's been a truly amazing experience getting to work with an electrical engineering team that designed the wireless monitoring system for the array, as well as an industrial engineering team that worked on the budget analysis for the solar farm.
Hi, my name is Ryan Lewis. I'm a mechanical engineering student here at UCF, and I have an emphasis in materials. And as previously mentioned, UCF in 2008 spent $12.5 million in electrical consumption costs yearly. And that number tends to rise 49% annually due to various reasons. Earlier it was mentioned that those reasons can vary from things like natural disaster, like what happened in Japan, and also the political situation in the Middle Eastern countries. So what is being done? As Dave mentioned, in 2007, President Hitt, along with other deans and presidents of universities around the country, they took a stand to be a climate-neutral campus by 2050, and that's zero net greenhouse gases. And according to UCF's Climate Action Plan, as Dave also previously mentioned, there's 5 steps. And in those 5 steps, there's energy conservation, energy efficiency, fuel switching, renewable energy, and carbon mitigation. And our project dealing with solar fits into the renewable energy category. Now, here's our design that is going to help UCF meet its renewable energy goal.
UCF owns around 1,400 acres. The site currently proposed as a location for the solar farm is a small 3-acre patch located off of Neptune Drive, past the observatory near the SAE shop. This land is free from obstructions and has good southern exposure. To accomplish our task of designing and building a mounting system that is cheap, simple, and easy to replicate, we designed a twin rail system with 4 vertical supports per rail, which holds 11 panels. To keep the structure anchored and meet Orange County Building Code, we used 16-inch wide by 9-inch deep concrete anchors. To meet the simplicity aspect, we used key clamps to connect all the support joints and rails. These utilize set screws which tighten onto the pipes and eliminate the need for skilled labor such as welding. The total weight of the system is around 920 pounds and measures roughly 40 feet by 5 feet. To achieve an optimal year-round collection angle of 29 degrees, the rails are set to different heights. The front one is about 1 foot off the ground, while the rear rail is about 3.5 feet off the ground. This creates a 29-degree angle, which is optimal for Florida for year-round collection. The panels are connected to the rails through the use of 2 simple custom-designed parts. The first being an aluminum bracket, which was adapted to fit the prefabricated holes on the panels and attach them to the rails. The second is a polyurethane bushing, which relieves any contact patches between the panels and rails and alleviates the risk of galvanic corrosion between the pipes, the panels themselves, and the brackets, and extends the life of the system, hopefully to outlive the panels themselves.
Hi, my name is Ryan Tribby. I'm a mechanical engineering student here at UCF with an emphasis in material science. 2 separate wind load analyses were performed in order to ensure that the design would not fail under possible 130 mile per hour 3-second peak gusts during a hurricane, as required by Orange County Building Code. In order to counteract this vertical lift and meet Orange County Building Code requirements, a soil analysis was performed at the construction site to determine the weight of the soil. The results of the soil analysis were then used to calculate and optimize the concrete anchors, or to calculate and optimize the proper depth and height of the concrete anchors to securely hold the support posts into the ground. In both instances, we found negligible shearing forces acting on the supports during our testing, as confirmed by wind tunnel tests performed on the photovoltaic arrays currently operating at Kennedy Space Center.
Hello, I'm Connie Griesmer. I'm a mechanical engineer with an emphasis in material science. Our team put together a final build video that takes you step by step through our entire build process from ground up. The location of the posts were first mapped out in order to ensure proper spacing between posts. A 2-man auger was used to dig each post hole, with each hole reaching a depth of 2 feet 9 inches and a total diameter of 16 inches. A total of 8 post holes were dug. A zinc-based cold galvanizing compound was sprayed on the ends of the cut pipes for further corrosion protection. Each pipe was then marked in order to ensure that the proper depth of concrete was used. The concrete was then mixed with a concrete mixer and then poured into the post hole around the set pipe for a total depth of 9 inches. The remaining 2 feet in the post hole was filled with dirt. The initial pipes were then leveled for accuracy and allowed to dry overnight. Once the 2 initial pipes were set, key clamps were added to aid in the addition of the next part of the module. The key clamps utilized set screws, which helped lock the pipes in place without the use of any welding. The remainder of the module was completed in a similar fashion by sequentially working from the previously assembled sections. The completed module was allowed to set for a full week to ensure stability. Marble rock chips were used as an overlay underneath the module to act as a barrier to any weeds that may grow tall enough to cast any shadows on the panels. The panels themselves were a total of 5 feet in height and 3 feet across. One by one, each panel was attached to the module by attaching a pipe bracket in each of the 4 corners of the panel. The pipe brackets were held in place by use of a simple nut and bolt system secured on the inner lip of the panel. The same process was repeated until all 11 panels were tightly secured to the module, thus completing the task assigned to the mechanical engineering team.
First off, I'd just like to thank you all for attending and having us today. We'd like to extend a special thanks to our financial sponsor, Dave Norvell from the Department of Sustainability and Energy Management, as well as our academic advisor, Nina Orlovskaya. We'd also like to thank our technical advisors, Patrick Robinson from the Florida Solar Energy Center, as well as James Nelson from the Kennedy Space Center. And of course, we'd like to thank the Department of Mechanical Materials and Aerospace Engineering, ECF. If you have any questions, we'll be at booth 25. And once again, thank you. And here's the electrical engineering team to discuss their wireless monitoring system.
Good morning, everybody. My name is Michael Gannon, and I'm an electrical engineering student here at UCF. I was part of the EE team assembled to design the solar panel monitoring system for the UCF solar farm project. As a team, we had many objectives when coming up with this monitoring system. First, we wanted the monitoring system to be able to sustain its own energy. This meant we didn't want the monitoring system to take any of the energy created by the 11-panel solar array and be consumed by the monitoring system. So to counteract this problem, we're going to use a small 24-volt solar panel next to the array, which will charge a battery bank that will be powering our monitoring system. Next, we're going to take the data wirelessly and transmit it to a land-based computer. This will be collected every 5 minutes for the duration of the day. The data then will be published online in real time in a format that is easy to understand and is publicly accessible.
Hi, I'm Ahmed Blaibel, and I'm an electrical engineering student at UCF. The panels we chose for our project are monocrystalline panels made by Sharp, and the model number is NUU240F1. We chose monocrystalline technology because it's the most efficient, which means the least amount of space will be needed per kilowatt, and because of their longevity of operation. Each panel will be producing 240 watts at 37.4 volts and 8.65 amps. The whole array of 11 panels will be producing 2,640 watts, and our design will monitor the voltage, temperature, and current of each panel individually and transmit the data wirelessly to a computer where we will upload the data into a website for real-time data.
Good morning, everybody. My name is Michael Peppers, and I'm an electrical engineering student here at the University of Central Florida. I'm going to talk to you about the design of the monitoring system. And for the monitoring system, we designed 2 individual circuit boards, one that will be mounted on each solar panel and another that will act as the data collection point for the entire array of solar panels. The printed circuit board that will be mounted on each solar panel will consist of 3 sensors that will monitor voltage, current, and temperature of each panel. The data from each sensor will be transferred to a data collection point through a 4-to-1 multiplexer and a Cat5e cable. A multiplexer, for those of you who don't know what a multiplexer is an analog or digital device that allows for multiple inputs to be transferred to a single output through software selection. This is the physical layout of the circuit board that will be located on the solar panels. The data collection point circuit board will house a 16-to-1 multiplexer that will select which panel to collect data from, as well as a microcontroller, optical relay switch, and a wireless communication device. The microcontroller will handle the data selection and the data transfer to the wireless device through software that has been developed for this application. The optical relay switch will allow for power to be cut to the entire monitoring system at night, so not to waste power when the solar panels are inactive. Thank you.
I'm Ali Khan, and I'm an electrical engineering student graduating this semester. I designed the wireless transmission system for our project. For wireless system, we used the XB Pro, which is a Zigbee network. And the reason why we chose this is because it's really cheap, and it's very good for the low data transfer. In our case, we're only going to have 3 readings: current, voltage, and temperature. So it's perfect for that. It has a good range for what we need. It goes about 1 mile outdoors, which is perfect because our solar panels are in the field by the UCF police station, and we're going to be monitoring in the next, the closest building. That's where we're going to have our base station. The connection between the XB and once we get the data to the microcontroller, we have to send the data. Data means the reading that we got from the sensors, to translate it and show it in some sort of graph or numbers that we can read. And we're going to be using 2 modules. One will be connected to a microcontroller at the panels, and the other one will be connected to a base station computer, which interprets all the data. And we can monitor the data live. As you can see, it shows the data activity each day of a month. You can check by day, by hour, by minutes, and it just shows you live data. This website is actually a real snapshot of our website, which is uploaded at the address given on the slide. That way we can monitor and save the data that we acquired from the sensors. And now I would like to thank our sponsor, Mr. Dave Norwell, and our technical advisor, Dr. Ritchie, and also Bob Rich, the coordinator for the symposium. And now the IEs are going to come and talk more about the further analysis of our project.
Thank you, Ali. And thank you, Dave Norvell, for this opportunity. We are the industrial engineering aspect of this project. This is my partner, Amanda Longman, and I'm Joshua McNaughton. Okay, just a basic outline of our presentation. Why photovoltaics at UCF? We're going to go over the goal of our project, as well as the prototype design as the mechanical engineer showed you. A little highlight from our forecast analysis, along with our project outcomes and some future considerations. So why photovoltaics at UCF? Well, some general reasons. Energy from the sun is renewable, and this renewable energy lasts about 25 years with the photovoltaic technology today. Some research has shown that it is starting to advance, and it could last longer than what's guaranteed at 25 years. It's also clean, environmentally friendly, and silent. Some UCF specific reasons. on-site energy production. We can produce energy right here on campus. Also, the capacity here at UCF has the availability to build photovoltaics on campus. And as mentioned previously before, President John Hitt engaged UCF in the President Climate Commitment. Thus far, in the United States, there's 677 colleges and universities who have signed on to this commitment, as well as 13 Florida colleges and universities right here in Florida. And you can see Central Florida right here.
I'd like to go over the industrial engineering goals of the project. We were tasked to conduct a feasibility study of constructing a 3-megawatt solar farm on the UCF main campus. Why 3 megawatts? That's what it's going to take to get to 15% of our energy production from renewable sources, which will help us meet our goals for the President's climate commitment that Josh just talked to you about. And to do this project, we worked together with electrical and mechanical engineering teams in a multidisciplinary project to construct a prototype. The other teams have already introduced you to our prototype. It features a sharp 240-watt panel, which we were able to save money on this high-quality panel by going with a local distributor, Superior Solar. This helped a lot because shipping costs for solar panels are usually as much as the solar panels themselves, and Superior Solar was able to deliver them to us without charge, so that was a great help to our project. The mechanical engineers developed a fixed mounting system, and this has minimal maintenance, which will be good for our project to minimize the downtime of the solar panels. It holds 11 panels, which are monitored individually by the electrical and communication systems that the EEs have just presented to you.
So this prototype will produce 0.003 megawatts, being only 11 panels. It's equivalent to taking a half of a vehicle off of the road, eliminates carbon emissions from about a third of a home, as well as eliminating carbon emissions from 117 propane cylinders like those used for home barbecues, saving UCF $283 a year. So what we want to do is take this basic design and turn it into a larger design. So we're going to transition from 0.003 megawatts into 3 megawatts. The requirements of this would be 11 panels will go to 12,000 panels. This will require not a single array, but 1,100 arrays. And the land requirements will grow from 240 square feet to 653,000 square feet, or about 15 acres. And that's a little bit more than 11 football fields. So if you take a look at this picture, you can see Bright House Network Stadium up at the top. Multiply that about 11 times on that undeveloped land here, and you can get an idea of how large this system is. So what this 3 megawatt system will do, it'll take approximately 623 vehicles off the road per year, as well as eliminate carbon emissions from the electricity use of 386 homes, and also eliminate carbon emissions from 132,000 propane cylinders like those used for home barbecues, saving UCF $322,000 a year from their energy bill.
One consideration with the implementation of this project is the variability in solar panel output caused by Florida's weather conditions. 3 graphs are shown here, and the one that's offset to the left a little bit is the best case scenario of a sunny day. The output increases as the sun rises, and then it decreases as the sun sets throughout the day. That's the best case scenario that we can expect from the solar panels. But in Florida, we have a lot of clouds, and as these clouds go across the sky, their shadows fall on the solar panels, and this decreases panel output. When the clouds move out of the way, the panel output goes back up. So that causes the up and down spikes in the average day graph shown in blue on the slide. And then we have some days in Florida where the sun doesn't come out at all. And that shows right at the bottom of the graph, there's a black line showing a cloudy day or worst case scenario of solar panels. So we need to understand how the panel output is not going to be constant or very predictable with the implementation of the 3 megawatt farm.
Another thing to consider would be the advancements in solar technology. This aerial shot of Progress Energy's experimental panels located on the corner of University and Econ Drive can kind of show the efficiency change over the years. These bottom 2 here are both producing 3.5 kilowatts combined. The panel right above that in the 3rd row is also producing 3.5, and the even smaller panel on top is producing 3.5 as well. So you can see how the efficiency changes over the years.
In summary, additional resources are going to be needed for the transition to the 3 megawatt solar farm for this project. We'll need more land, more materials, and a larger monetary investment. And this study is in support of the President's climate commitment to become a carbon neutral campus by the year 2050. And the success of this project is due largely to the multidisciplinary nature of this team with mechanical, electrical, and industrial engineers working together. To recap, the mechanical engineers have designed a mounting system which is fixed and requires minimal maintenance. The electrical engineers have designed a monitoring and wireless communication system that will show panel output in real time. And the industrial engineers have looked at the prototype, kept an eye on cost, and had interviews with industry professionals to come up with a design forecast for the 3 megawatt solar farm. We'd like to thank Dave Norvell and his assistant, Gina Spahi, our faculty advisors, Dr. Geiger, Dr. Thompson, and Dr. Ritchie, and the electrical and mechanical engineering teams who have presented before us. And we'd also like to extend our thanks to the corporations whose representatives have advised and assisted us throughout this project: Progress Energy, Kennedy Space Center, Florida Solar Energy Center, and Superior Solar.
Thank you.
My name is Long Wing, and I'm a mechanical engineer, and I will graduated this fall of 2011, and this is Sean and Brian, my teammate. And the purpose of this project is to provide safe drinking water for developing country, and to accomplish this, we heat the water to kill the bacteria, and this is to create a simple design that can be done by people. How this works is that a parabola has a focal point, and the sunlight is reflect and concentrate to that point, and if you extend it to 3D, and then it will become a trough, so that we run through a pipe through it, so that the water can flow through that, and so in that way it can be heat up.
Hello, my name is Sean Seberg. I'm graduating in May 2011 and with a bachelor's in mechanical engineering. Some of our project goals is to heat the water to essentially 100 degrees, which is boiling point. We also want it to follow the sun throughout the day, and we also want to be able to heat up 500 liters. Another project requirement was for us to have 3 months of no maintenance, and we have a video of it working. You could see both troughs move together. We have a lot more videos at our booth, so when you guys could stop over, we're in the corner back here. Now I'm going to give it to Brian.
Good morning. My name is Brian Sunholm, and I'll be graduating this May with my bachelor's in mechanical engineering. There are definitely a lot of uses that you can use with solar thermal heating. Radiant heating, for instance, you can heat your house using evacuated tubes running through your walls and floors. You won't notice a significant difference in the heat, but it'll definitely save some money in your electric bill. It'll also heat up any kind of hot tub, swimming pools. On average, your hot tub will use about, it'll cost about $300 to $400 extra a month on top of your original electric bill. By using this to heat your hot tub, it's pretty simple considering it's a small amount of water. The same goes for the washing machine. It's definitely, we're not using any kind of gas engine or anything to use this, so it doesn't have any exhaust to pollute the air. The energy is renewable, and it requires very little maintenance after only 3 months. At this time, I'd like to thank Dr. Nina Orlovskaya for all of her support and patience throughout this last year, and of course Progress Energy for the funding to complete this project. If you'd like to ask us more questions, we're at the booth on the far right side over here, and the organic Rankine cycle group is up next. Thank you.
Good morning. Our design project was the solar organic Rankine cycle system. We've named the system the Prometheus Alpha. The Prometheus Alpha system is a small-scale, portable solar organic Rankine cycle system that we've designed so that it can be used in lieu of traditional diesel or gasoline-powered generators. It implements an organic fluid, which is where the organic part comes into play, which is a hydrocarbon called pentane, liquid at room temperature, but boiling at about human body temperature. This means that you can use a heat source like the solar trough group's hot water that is higher temperature, but it's a lower initial heat input. How the system works is basically there's a phase change that happens, and the pentane boils and reaches its vapor state. The vapor state causes a pressure difference, which turns the turbine. The turbine creates mechanical work, which an alternator turns into electrical energy. The system is very versatile and scalable, and it's able to use geothermal, industrial waste heat, and other solar heat sources.
Hello, my name is Paul, and I am a mechanical engineering student here, and I will speak briefly about the intended purpose of this system. Prometheus Alpha is marketable as an alternative to portable internal combustion generators. It can be used at the personal level in a variety of different situations, such as power outages, natural disasters, and remote living. Because it can be adapted to work with different heat sources, this system is practical for use with industrial waste heat to generate additional power. And on a larger scale, a system like this could supply power to a temporary grid in remote locations.
My name's Benjamin. I'm a mechanical engineer. I will be talking about the methodology of our project. In essence, it's a turbine-based electrical generator, which can be portable and efficient. Energy is provided by solar heated water, so there's no refueling or no combustible fluids out of the system. It would create about 100 amps of AC current, create enough power for small electrical devices. It's assembled from standard components. In our case, it was car parts, and is designed to be completely scalable and low maintenance.
My name is Michael, and I'm also a mechanical engineer, and I'll be giving a brief overview of what our current prototype is able to do. As of now, our overall design is sound, and we have about 90% of the prototype in working order. The heat exchangers only require an input of about 45 degrees C of water in order to get our working fluid into its phase change of vapor. And for the condenser, we're looking at about 16 degrees C of water, which could also be adjusted maybe a little warmer. As of now, all the pumps in the system, including the water pump, fuel pump, are all working, not creating any turbulent flow throughout the system at all. And all electrical components are in working order, providing the electricity that we need to power any household items, as well as the recharging.
My name is Kenneth Hart. I'm a mechanical engineer, graduating in 2011, December 2011, with mechanical systems. I'm here to talk about some of our future modifications, some suggestions we may have for groups that are doing later generations of our project. First is develop a turbine specifically for the organic Rankine cycle, one specifically that's airtight, so we don't have any leakage like we would with the car turbocharger. It also is desirable for it to have its own internal power generator. That way we can do away with the alternator. That leads to utilizing components specifically designed for the organic Rankine cycle system for better efficiency and performance. Improved seals and fittings for the hoses and piping, and also enhanced control systems for the pumps and electrical systems would also need to be developed. We did stay under our self-imposed weight and size limit of a 400-pound system that was easily transportable in the back of a small pickup truck, but we could develop it lighter. The system could be made lighter through use of lighter components or lighter materials, stuff like that. If you got rid of the alternator and it's just sheet metal, composite materials, we can definitely cut our weight in half. All right. We'd like to say a special thanks to our advisor, Dr. Nina Olovskaya, as well as Progress Energy and UCF for all their funding and support. Thank you.
All right, good morning. We're the Solar Balloon System Group. Our project head is Dr. Lin, our technical advisor, Dr. Deng, and our faculty advisor for senior design is Dr. Shu.
And I am Jared Clark. I'll be graduating this May with mechanical engineering.
I'm Alex Gardner, aerospace engineering. I'll be graduating this May.
My name is Kyle Little, and I'm a mechanical engineer, and I'll be graduating this May also.
My name is Mark Livingston. I'm a mechanical engineering major here at UCF, and I will be graduating in spring of 2011. For this project, I focus mainly on the materials and the scale environments.
And I'm Leah Van Leer, also mechanical, graduating this May.
Our solar balloon design is essentially based on SunHub's balloon system, which is an award-winning design for the past couple of years. And the essentials of this design is helium-filled platforms on which rest photovoltaic arrays, which collect sunlight and then distribute it as needed. The reason this is such an appealing system is because of its simple infrastructure, namely All you need are a control panel, a helium supply line, and a power cable to gather electricity for this.
There are many benefits of using a solar balloon system. The first of which is that they have the ability to collect more direct and diffuse sunlight when compared to more traditional solar collection systems. This is mainly because balloons are spherical in shape, which results in an increased surface area. They also have the ability to collect light over a 360-degree range. The solar balloons are also low maintenance. Theoretically, once the balloon is initially set up, it will require no maintenance for a period of 1 year. They are also inexpensive. The SunHope company aims to produce the same amount of solar energy a traditional photovoltaic array produces for $4,000 compared to $10,000 for the traditional photovoltaic array. Solar balloons are also portable. They can be deflated and easily transported from one location to another. And lastly, they are beautiful, as you can see here in this artist rendering.
Okay, this brings us to our project. Our project was not to build an actual solar balloon, but rather test the concept of the solar balloon, and in particular test how the solar balloon would react to being placed in different environments. In the picture you can see right in there is our solar balloon model. We built a miniature solar balloon model outfitted with solar panels, and Kyle will talk more about that in our next slide. Above that model you can see our light source, which is inside that lens housing, and it's supported by an aluminum structure which pivots around one point. This aluminum structure allows the lens housing to rise and fall like the sun, and it also pivots to accommodate any location on Earth. The final product, which it will not only act as a testing system to further the development of the solar balloon, but it also will act as a mobile presentation piece.
Also, as he talked about, we have different environments that we modeled of the Orlando area, and we tried to make them as realistic as possible. As you can tell, in this one we have a lake environment, which is done after Lake Pickett. We also did a downtown environment, where you can see at our booth a little bit later. And also you can see right here we have our solar cell, our solar balloon, and our solar balloon contains 8 solar cells that are arranged on there. And the solar balloon itself is hooked up to a DAQ, which the DAQ then reports the voltage that it's been receiving from these solar cells and recording it onto the computer. Each of the environments is going to be recording a different value, since each of them is going to have different reflective values on them. Also, we have our Fresnel lenses here, and the importance of those is that we need our light rays to be parallel. And in order to do that, we needed our Fresnel lenses to make them parallel so that we can have our light source act more like the sun.
All right, so as we said, this is still sort of in the building stages, but as far as applications for a full-scale solar balloon, because it's so portable with a simple installation, there are many. They're useful in a variety of locations, especially those with space constraints. For example, a city where you don't want to build outward for your power source, you can build upward and float balloons off the top of buildings. Also off-grid applications, so over bodies of water or dense forest. And since they're aesthetic, they're more likely to be used in a city where they're highly visible and to meet the approval of homeowners associations. And again, since they're so easy to move and set up, they also have potential applications as an emergency power source in natural disasters. So we'd like to acknowledge Progress Energy and the UCF Droplet Energy Lab for their help, and we hope you come visit us. Thank you.
Thank you.
All right, good morning, distinguished guests, faculty, and students. My name is Nate Boyd. I'm a lead AP, mechanical engineering graduate here at UCF, and I now serve as the energy manager for the city of Orlando. I am also the student activities chairman for the Central Florida chapter of ASHRAE. For each of the last 5 years, UCF has competed in ASHRAE student HVAC design competition with other universities from around the globe. Last year, our ASHRAE UCF student team won the design competition, giving UCF its 3rd ranking in the top 3 universities in the last 4 years, and our first win against colleges like Purdue, Cal Polytechnic, Kansas State, and the rest of the engineering powerhouse universities. UCF and ASHRAE share a special relationship. ASHRAE's research is at the very heart of sustainable building design, and our Central Florida chapter invests heavily in our UCF student branch through mentoring sessions that provide the students with the tools to practically apply the knowledge they gain from their studies, scholarships, and internship opportunities, empowering them to enter the workplace with the skills to go out and make a positive impact on the built environment. Without further ado, it is my pleasure to introduce the ASHRAE HVAC selection team, followed by the ASHRAE HVAC design team. During this session, you will also hear presentations about an environmental wind tunnel project, hydraulic regenerative braking, and a fuel cell powered UAV. Thank you.
Good morning, everyone. We are actually the ASHRAE system design team. I guess there was technical difficulty. Instead, we will be going first, and the system selection team will be following. We are, as Nate Boyd just said, the participating in the ASHRAE International Design Competition. Our faculty advisor for this project is Dr. Illy. Technical advisor was Nate Boyd, who you just saw. We have myself, William Bradford, Dustin Yoder, Daniel Cronky, Orion Dominguez, and Matthew Basnight. Okay, so first, what is ASHRAE? ASHRAE is the American Society of Heating, Refrigerating, and Air Conditioning Engineers. It's an international organization in over 130 countries, and it has over 51,000 members. ASHRAE is very important because it helps provide guidance for the U.S. government in establishing the energy guidelines for their federal buildings. ASHRAE's mission is to advance the arts and sciences of heating, ventilation, air conditioning, and refrigerating in order to serve humanity and promote a more sustainable environment.
And our project's part of the 2011 Student Design Competition. The competition requires us to design a HVAC system for the Drake Well Museum. HVAC stands for heating, ventilation, and air conditioning. The Drake Well Museum is a 20,000 square foot building located near Titusville, Pennsylvania, and home to the first oil well. This project requires us to calculate all the necessary heating and cooling loads in order to properly size and select our HVAC equipment and systems to provide an energy efficient design. Also, our design must meet ASHRAE standards for comfort, ventilation, and efficiency. Also in this project, we were required to fulfill specific owner requirements, such as a budget we were given of $2.4 million for all of the mechanical, electrical, and plumbing. Also, because our building is a museum, we had to maintain specific climate control in order to preserve all the museum's artifacts. Also, our design had to achieve LEED Silver. LEED stands for the Leadership in Energy and Environmental Design. LEED is a point-based certification system rewarding energy and environmental conscious design elements. Some examples of this: all the new construction at UCF since 2007 must be LEED Silver. Also, the new Amway Center in downtown Orlando is LEED Silver.
Okay, for our project we use Building Information Modeling, or BIM. A BIM model is essentially a virtual model of the building that has both architectural and mechanical aspects. The software we use to create this BIM model is called Autodesk Revit. Now, there are two main features of the software that greatly benefited our project. First is the software's capability of analyzing each space within the building and generating a very detailed building summary. Within this building summary, the most important aspect is the heating and cooling load calc, so overall for the building. We use these basically to determine the correct size of our system. The second aspect of this software is the ability to place each component of our design within the virtual model. This allows us to determine the correct length of duct, the correct length of refrigerant, the volume of refrigerant that we will need for the entire system, and whether or not if the system will fit in the space we have provided.
Okay, so I'm going to talk to you guys a little bit about the system type we decided to go with. It's known as a VRF, or Variable Refrigerant Flow System. VRF system is a split heat pump system with a single condensing unit and multiple air handlers located throughout each building zone. It intelligently varies the flow of refrigerant to each of the units, and it also allows heat to be transferred from one room to another. Part of our owner requirements is that we meet ASHRAE standard 189.1, which is the standard for high efficiency in green buildings. That standard calls for an EER rating of 12, and for our system we have an EER rating of 13, so we meet that standard. Another great reason we chose to go with this system is that it's a single system solution. Originally, we were looking at doing, maybe a boiler or something to heat the coldest days of winter, but the heat pump system we're using can operate down to -4 degrees Fahrenheit, and therefore more than meets our temperature requirements. This is a schematic showing a basic VRF layout. As you can see, you have one condensing unit, which then goes to a controller, which varies the refrigerant flow to each of the indoor units.
We also took the opportunity with this project to provide some local power generation through wind, using a small commercially available wind turbine that uses the latest in blade tip power generation technology. Basically, this unit, instead of having a fancy gearing system at the hub, it uses the higher velocity at the tip of the blade to generate that power directly. And with this, you get a much bigger working range, or a much lower working range with the wind. As you can see, starting at 2 miles per hour, all the way up to 38 miles per hour, giving you a better amount of power generation. These units are fairly cheap, with a net installed cost of $6,700, and that's after $3,000 in federal and state incentives. And based on some wind data that we pulled from NASA, for our area, we'd be able to generate 1,300 kilowatt hours annually per unit. And the payback for these units is just 8 years compared to 11 years with photovoltaic cells. And it's estimated these could save up to 13 tons over their lifetime of CO2, 15-year lifespan.
Once again, going over it, we had Matthew Basnight, who presented the VRF units. He is going through the materials option. I, myself, William Bradford, I'm doing the energy systems option. I'm the president of ASHRAE at UCF. Dustin Yoder, Daniel Cronky, and Orion Dominguez are all doing mechanical systems. For this project, we would like to give a special thanks to the Central Florida chapter of ASHRAE for all their help, and our technical advisor, Nathaniel Boyd. We'd also like to thank the companies on our slide. For more information on our project, we highly encourage you to come to our demonstration booth, and we'll give you a better idea of what's going on. Thank you all so much for listening.
Hello, we're here to present our project, the Fuel Cell UAV. With me today is Nathan Fist, Joseph Breitenbach, Curtis Schneider, Adriano Rampolla, and Lauren Ferlita. We're all aerospace engineers, so this is a very dear project to us. If you haven't already stopped by, our post is up in the back. You can find us easily. We're the only ones here with a plane. So I guess we'll get started here. The purpose of this, we wanted to design an unmanned aerial vehicle to be powered by a hydrogen fuel cell. More specifically, our goals were to achieve stable flight, including takeoff and landing, and to fly for a duration of 2 hours using the hydrogen power.
Hi, I'm Nathan Fist. This is a picture just to give you an idea of how big our aircraft is. It's got about a 10-foot wingspan, and it's about 5.5 feet long. The wing and the tail are made of foam covered in carbon fiber, with the wing that has a carbon fiber rod through the middle for extra strength. And the fuselage and the booms, including the back landing gear, is also carbon fiber. And with all the fuel cell and hydrogen tank and all the other electrical components, it's about 26 pounds, and it can fly about 30 to 40 miles per hour.
I'm Curtis Schneider, and I'm an aerospace engineering major. I'm going to talk to you about the applications of this fuel cell UAV. Currently, UAVs are used in the military for combat and surveillance. Also, President Obama and our government have recently employed a group of UAVs to watch the border between Mexico and the United States. This fuel cell UAV can be used for both these applications, along with crop monitoring, oversea oil well monitoring, and recreational use. Hopefully one day this technology will trickle down and want to be in our automobiles.
Hi, I'm Lauren Ferlita. I'm going to be talking about the driving factors of our project. The main factors are environmental pollution, such as noise pollution, pollution from the fuel and exhaust. An interesting quote is, Charles Lindbergh ended life regarding air travel as mere squalor, and aviation in general is one of the world's serious environmental problems. We have a couple facts to further show these environmental problems. The first one is the pollution from one 747 2-minute takeoff is equal to operating 2.4 million lawnmowers simultaneously. That's a lot of lawnmowers and a lot of pollution. Also, jet fuels are responsible for about 3% of overall U.S. carbon emissions and is expected to grow 60% by the year 2025. And the fuel cell that powers our UAV, the only byproduct is water, so it makes it a great alternative to power use today.
Hello, I'm Joe Breitenbach. I'll be talking to you about the advantages of using something like a fuel cell for a power source. The first would be efficiency. The unit we're currently using is a 200-watt PEM fuel cell. It's approximately 40% efficient at its rated 28 volts. If you turn your attention to the graph on the screen in front of you, you can see that fuel cells have a very wide output power range. And associated with that is still very good efficiency. You'll notice that down in the bottom is gasoline electric, right above that diesel electric. Typical internal combustion engines reach approximately 25 to 35% depending on applications. Steam and gas turbine engines are far better, but still fuel cells are in their infancy, so even a commercially available fuel cell today would still be able to most likely surpass them in the future. Next is low maintenance. All we have to do to keep our fuel cell maintained is to properly hydrate it because of the membrane inside. So very low maintenance and not much associated with cost on that. Just use distilled water, run it through the fuel cell, blow it out with excess hydrogen, and you're ready to go. The next would be fuel weight. Hydrogen is a very, very light gas. If you look at the periodic table, it's up in the top left. So really all your weight would come from the actual storage tank or storage vessel for the hydrogen as opposed to the fuel, whereas a hydrocarbon fuel is far more dense. The next would be fuel flexibility, obviously keeping with the values of Progress Energy, trying to get us away from fossil fuels. Hydrogen is a viable option, and it can be produced in a very renewable and sustainable way. You can produce it through certain biomasses, such as algae, and electrolysis if you use a renewable energy source such as wind power to power that facility. And the last thing, when set up properly, they can be very less susceptible to structural weakness or corrosion. A lot of our fittings are rated for hydrogen, and the tubing used is something like a silicone grade, very safe, and no structural weaknesses, especially when the fuel cell is designed to run hydrogen.
All right, well, good afternoon, everyone. My name is Adriano Rampolla, and at this time, we would like to show you a short video that features segments from one of our more recent test flights. And particularly it features onboard video from our aircraft. Just some information about our test flights. We fly out of an airfield in Apopka, which is owned and operated by the Remote Control Association of Central Florida. It's probably about 50 minutes from here. We had 3 different test pilots fly our aircraft. Each one was an AMA certified test pilot, and each pilot has a specialty. For example, one of the pilots likes to fly gliders, whereas another pilot was a world-renowned pylon racer. So each pilot put our UAV through a different type of flying. Some were more aggressive, some were more conservative, and overall we conducted about 6 or 7 different tests. And our UAV is still flying, so thankfully it passed every test. And this is just some of the scenery around the airfield in Apopka. And thankfully it landed. And it's still in one piece. Okay. We'd like, on behalf of myself and my fellow teammates, I'd like to personally thank Progress Energy for their contributions to our project. The film you just saw would not have been possible without the funding that they gave us. We would also like to thank these other companies, Praxair, who supplied us with a hydrogen system. Zon Electronics supplied us with the electronic converters that we needed to be able to incorporate the fuel cell into our setup. Horizon Fuel Cell Technologies, they made the fuel cell, the airfield. And most of all, we want to thank our advisor, Dr. Youngjun Ju. He has helped us countless hours he spent helping us get through a lot of obstacles. So thank you for your time. We hope you enjoyed our presentation, and feel free to check out our project during the break. We're in the back left corner over there. So thank you.
My name is Bill Wynn. I'm a senior mechanical engineering student.
and I'd like to introduce you to the hydraulic regenerative braking team. First thing with our project is to develop the need for hydraulic regenerative braking, and as you can see, with over 250 million vehicles registered by the Department of Transportation in 2008, that there's a great need for a better fuel efficiency amongst that fleet. With most automobiles, the brakes don't utilize this energy, they actually waste it in the form of heat. So what hydraulics do is they provide a method of capturing the majority of this energy in an efficient manner. This has been tested with UPS and developed a system that was able to incorporate over 40% increase in fuel efficiency. And in addition to this, there's no current parallel systems for a smaller scale like truck or like minivan. And one of the really cool things about our project is companies such as Chrysler, as of January, just announced that they were going to start a research and development team to make the town and country car actually implement a hydraulic hybrid system, much of that like what we're doing here.
Hi, my name is Mark Donahue. I'm a senior mechanical engineering student and I'll be graduating in May. I'd like to give you a little background on what exactly hydraulic regenerative braking is. So as Bill mentioned, this has the ability to capture energy normally lost in braking in a usable form, and this is accomplished through connecting a pump to the existing drivetrain of the vehicle. So as the vehicle is running, it has kinetic energy, and that kinetic energy can be used to power the pump, which charges a high pressure accumulator. So that resistance to that accumulator being charged effectively slows down the vehicle, bringing it to a stop. Then upon stopping, the pump can be reversed, switching the input and output ports, and the fluid can be forced back through the pump, spinning it in the same direction of travel of the vehicle and propelling it forward.
I'm Stephen Hampson, a senior mechanical engineering student. So our biggest competition in the world of regenerative braking is electric regenerative braking. In comparison to hydraulics, it has a much lower power density, so the weight of the batteries in comparison to how much energy they can hold is pretty low. Also, these electric systems require specialized technicians to work on them. An average automotive shop would not be able to handle these. And because of the capabilities of today's technology, we're not able to completely harness the braking power through the electronic systems, so some mechanical aspects must be utilized, which decreases the efficiency of the systems altogether. Hydraulics, on the other hand, have a much higher power density. They're very easily scalable to larger and smaller vehicles, and also the materials being used are much more environmentally friendly. For our project, we converted a gas-powered golf cart into a hydraulic drive vehicle. In order to do that, we first had to fix the vehicle, which was inoperable when we gave it to us, and perform some initial benchmark testing on the fuel efficiency of the vehicle.
All right, so here are a couple of main decisions we made in constructing our hydraulic system. The first of which is the overall system configuration. We chose to go with the parallel design, which kind of connects and assists the existing drivetrain of the vehicle. So this allows for the system to kind of just assist rather than replace the existing drivetrain. This makes it more adaptable, and it also allows the existing drivetrain to kind of still exist in case of a failure or something like that in our system. For the pump, we chose a variable displacement over center pump that can be fully reversible. So this means that a single unit can handle the capture of the energy as well as the return of the energy to the vehicle. This limits the complexity of the design and the number of components, and also allows for more control. So with a variable displacement, you can change the torque values and things like that that are output by the pump. Finally, the accumulator chosen was a piston type accumulator, and this is as opposed to a bladder type accumulator. This was chosen for a couple of different reasons. The first of which is that it's kind of more safe in operation, so that the failure modes is a more gradual failure, so it can be recognized and remedied before catastrophic failure of the system. And in addition to that, it is able to be mounted in a more variety of orientations, so that given different applications that don't allow for it to be oriented upright or things like that, the piston accumulator would be a desirable component. So the goals and requirements of our system is first to be able to capture that energy that's normally wasted in braking, and then be able to use that energy in the acceleration of the vehicle. And in addition to that, it also needs to be safe during operation, so there's a lot of high pressure components and things like that that are involved, so it needs to be able to operate safely and cause no hazard to the driver. And this is achieved through redundant safety systems like relief valves, and the existing mechanical brakes are still left in the system, so in the event of system failure, it can still be stopped. Additionally, we don't want the driver to have to do any more operations while driving to adjust the driving style or anything like that. So all of the inputs to the system have been incorporated to the existing pedals. Finally, it needs to provide adequate braking power, and this is determined based on the vehicle's stock braking power. So we need the vehicle to be able to stop within a given distance to avoid hazards and things like that, and not compromise the safety of the vehicle in that sense.
So for our final project, we were able to take the components listed by Mark earlier and kind of generate like a little rundown with the Parker pump we chose. That was a variable displacement pump that was able to generate electricity in both ways, or store the energy. As far as our accumulator goes, we were able to take the full maximum velocity and slow the vehicle, storing the majority of our 27.4 kilojoules of energy and generating a roughly 2,500 psi. In addition to that, we also were able to get the braking to match that of the current vehicle that before modifications with benchmarking, and of course we were able to get the efficiencies up later through controlling the pump and fine-tuning our controls. We'd first like to thank Progress Energy for funding, and also Dr. Nina Orlowskaya for her advice and support. In addition to which, we'd like to thank John Thomas of Parker Industries, who was able to help us verify our design and look over some of our component decisions, and Hydraulic House of Orlando, who was able to fit and pipe all of our system. And then when you guys go home tonight, I'd like you to think the next time you hit that red light that all that energy that you could be saving using hydraulic regenerative braking. Thank you.
Good afternoon, everybody. Thank you for coming out today. We are the environmental wind tunnel team. Our group consists of Anthony Bravado, David Giesick, Chris Gonzalez, and myself, Joseph Butera. I'm a mechanical engineering student, and I'll be graduating at the end of this semester. Renewable energy constitutes approximately 10.5% of the total energy generated in the United States. Wind energy constitutes 16% of all renewable resources. In the 5-year span from 2005 to 2010, wind energy grew 515%, and projections indicate that we should see that growth sustained in the future. As with any mechanical system, wind turbines are going to require repairs at some point in their lifetime. Blade issues constitute 34% of the annual downtime for wind turbine repairs. Leading edge erosion is one of the leading causes of blade failure. Given the significance of blade repairs, research into advanced coatings to improve the lifespan of wind turbine blades is needed.
Hello everybody, my name is James Ingram. I'm a mechanical student here, graduating in May, thank goodness. Based on what my colleague was saying, we have the ability to potentially save a lot of money by reducing the downtime of wind turbines associated with blade fatigue and blade erosion. And one of the problems we have regarding this type of research, increasing the durability of turbine blades, is we encounter some unique problems. Those include difficulty of access to blades in the field and very hazardous conditions as well. And the time periods required for degradation to occur in the field are too long to provide any type of quantifiable data. In order to effectively test wind turbine blade erosion in a laboratory setting, we need to be able to achieve accelerated degradation of materials, and we are able to promote that with a wind tunnel by injecting particulate into the flow to simulate coastal and desert conditions.
My name is David Giesick. I'm a mechanical engineering student. So with what James was just saying, to achieve the requirements, we needed to build a wind tunnel. And you can see here, this is our computer automated design, and this is our final product. Our tunnel is capable of wind speeds of 45 meters per second, which is approximately 100 miles per hour. We're able to simulate desert conditions using our sand injection system. We are also able to simulate ocean conditions using our saltwater injection system. We are also able to have uniform particulate flow thanks to our adjustable nozzle system, as well as the well-conditioned flow thanks to the proven design that we used.
Hello, my name is Anthony Bravado. I'm a mechanical engineering student. Even with the environmental wind tunnel's ability to test advanced coatings, we still are unsure of the financial advantages. In an attempt to quantify the potential for savings through advanced coatings, we performed a cost-benefit analysis. In his research entitled Assessment and Optimization for Operation and Maintenance of Wind Turbines, Dr. Rademacher analyzes the financial aspects of an idealized wind farm. Given the detailed and comprehensive nature of his work, we chose to use Dr. Rademacher's data as the basis for our cost-benefit analysis. The simulated the simulated wind farm consists of 86 megawatt turbines, or wind turbines, giving us a 480 megawatt rate for the total farm output. The study uses the Dutch offshore wind energy converter, or DOWIC model, to estimate turbine blades to give approximately 160 hours of downtime per year. And in the year of this publication, 1 kilowatt per hour cost 11 cents US dollars.
Hello, my name is Christopher Gonzalez. I'm an aerospace engineering student, and I'm graduating in exactly 28 days. Not like anyone's counting or anything. Now, when the cost per kilowatt hour is applied to the time lost due to wind turbine blade downtime, a total revenue loss of $8.5 million per year is accumulated. Now, after applying a material blade coating, a decrease in downtime of the turbine blades can be expected. We simulated a conservative assumption of 5% decrease in downtime. In the graph displayed, you can see the difference in the amount of revenue lost between a wind turbine farm of non-coated blades versus coated blades. With the 5% decrease in downtime, the total revenue loss is $7.2 million. Now remember, this is opposed to the $8.5 million with the non-coated blades. In conclusion, what this means is a wind farm of coated turbine blades with a minimal reduction of downtime will save an annual $1.25 million compared to a standard wind farm. And on behalf of UCF and the College of Engineering and Computer Science, we would like to give a special thanks to Progress Energy. We would also like to say thank you to our technical advisors, which would be Dr. Go and Dr. Kapat. And if you have any questions as far as how we calculated our values and how we plan to save money in this energy field, feel free to come see us. We're directly behind you, and we have our test section there for you to come see. Thank you very much.
Good afternoon. My name is Richard Villanueva. I am a senior mechanical engineering student here at UCF, graduating in May. I'm here to present you our submission to the 2011 ASHRAE International Design Competition, system selection for the Drakewell Museum in Titusville, Pennsylvania. ASHRAE is a society of heating, refrigeration, and air conditioning engineers. Founded in 1894, this international organization has over 51,000 members, which consist of engineers, architects, and contractors. ASHRAE is responsible for providing guidance for the U.S. federal government to establish energy guidelines per building.
I am John Foley. I am also a senior in the mechanical engineering program, and I am set to graduate after the summer term. As Rich said, we are competing in the 2011 Student Design Competition. This competition is taking place at the Drakewell Museum located in Titusville, Pennsylvania. The purpose of our competition is to select the best HVAC system for this museum, keeping in mind that we have a budget of $2.4 million, $500,000 of which is dedicated to the building envelope. Basically what a building envelope is it's any way that heat can get into or out of a building. Everything from the roof, walls, windows, basically any way you're going to get heat transfer. We are the system selections team. We're going to design and select the right size HVAC system. HVAC, by the way, is heating, ventilation, and air conditioning. A system that's too large for a building can be just as inefficient as an undersized system. We're going to be reviewing 3 different systems for this facility, which Nate will be taking you through in just a second here. And we're going to be looking at these 5 different criterion to determine which system best fits this facility.
Good afternoon. My name is Kenrick Barnes, and I'm a senior here at UCF, studying mechanical engineering with emphasis in mechanical systems. Before we talk about the three systems that we've chosen for our project, we'd like to talk to you about building information modeling, or known as BIM. BIM allows us to create a 3D model from 2D architectural drawings. BIM makes it more convenient to determine heating and cooling loads required to condition the different spaces of a building for people to be comfortable. These loads are then used to properly size the heating, ventilation, and air conditioning systems. Energy modeling is also considered to decrease thermal load and increase efficiency. By implementing a newer standard by ASHRAE, standard for high-performance green buildings, we are able to reduce their thermal load by 20% just by using this standard.
My name is Nathaniel Tallman. I'm a mechanical engineer specializing in energy systems. I'll be graduating this May, so I'm for hire. This is our first system right here. This is basically it comes down to conditioning the air in the room and keeping it clean. So this system is called a rooftop direct expansion system. And basically what it does is it's outside, it be on the roof, like on a commercial building, and it's the easiest for maintenance to work on, and it has lower initial costs than our other two systems, the chilled water / boiler system and the variable refrigerant flow system. The VRF system, otherwise known as the variable refrigerant flow system, basically sends refrigerant to different zones in our building, and so it can have simultaneous heating and cooling. It can also cycle on and off to meet the demands of the room. Our last system is a hydronic system. It's a combination of a chiller and a boiler, and basically it heated or hot or cold water is pumped to different parts of the building, and this allows us to adjust the temperature. It has better indoor air quality than the VRF and allows more zone control than the DX system.
Our final recommendation for the building was the variable refrigerant flow system. And this was due to two main factors. It was the 25-year life cycle cost, which took into account the initial cost, the energy consumption, and the maintenance of the system, and also how energy efficient this system was. The graph that you see on the bottom there is the 25-year cost. It was pretty close between the variable refrigerant flow and also the rooftop direct expansion. The main benefit from the variable refrigerant flow was that it was more energy efficient, which means that over this 25-year cost, or over this 25-year time period, the building is going to be consuming less energy. It's going to be a more green building. And also, this is just at 25 years. So as you look out into the future, the energy efficiency of the system is just going to continue to save money for the building.
All right, and again, I'm Richard Villanueva, John Foley, Nathaniel Tallman, and Kenrick Barnes. We just wanted to give a special thanks to our faculty advisor, Dr. Illy, our technical advisor, Nate Boyd, energy manager, City of Orlando, and also to the other companies that helped us along the way on the slide. Thank you.
Good afternoon, everybody. My name is Van Trong, and I'm a senior in mechanical engineering. These are my colleagues Sung Kim and Andrew Sean. And we're here representing the MMAE department under our advisor, Dr. Su. And our project's going to be on regenerative braking and supercapacitor boost. So first, why do we do this project? Well, we all know from the conservation of energy law that energy cannot be destroyed. So when you're driving in your car and you hit the brakes, where is all that energy going? Well, most of it's actually converted into heat energy through friction on the brake pads. That heat energy is pretty much dissipated into the air and is essentially wasted. So now if you think about how many times you hit your brakes on your daily commute and you multiply that by the amount of cars that are actually on the road, there's a substantial amount of energy that's wasted. So what can we do? Well, ideally, we can recapture, recycle, and recharge this energy. So the big question would be, how do we accomplish this? And our answer to that is regenerative braking. Regenerative braking essentially is just converting kinetic energy into electricity that we can use. This is possible because of duality of electric motors. Pretty much, when you put current into a motor, it spins in a certain direction, and when you manually spin a motor, you actually generate electricity. So in a regenerative braking system, when you hit the brakes, not only do the friction pads close, but the motor actually reverses its poles and causes a reverse torque, and that counter torque slows down the car. So now regenerative braking is already found in state-of-the-art technology in electric vehicles, but what makes our system unique is our use of supercapacitors. And Sung is going to tell you about the supercapacitors.
Hi, my name is Sung. I'm a mechanical engineering student in the mechanical option in my senior year. The reason why we decided to use supercapacitors was because that batteries are a lot limited in their charge and discharge rate. You can only charge them at a certain rate and discharge them before you degrade them. And capacitors can charge and discharge instantaneously. They can also have a lot more life cycles. About the supercapacitors we use had about 1 million cycles. Capacitors also have the way we hooked it up, we have an on-demand boost function, where the energy is gathered and then we can press a switch to discharge the energy. This works in a way similar to Kodak cameras, where if you want to take a flash, you press the flash button and then that charges a capacitor up, and when you take a picture, it releases that energy. Same way it works in our system as that when we brake or when we let off the accelerator, the energy is captured to the capacitor, and then when we press a button, similar to the flash, it releases the energy for boost. Some of the goals of our project, the main goals were to obviously recycle this braking energy into usable electricity. As I said before, we're trying to integrate these supercapacitors effectively into a regenerative braking system to provide boost. And we use a small go-kart as a test platform because this is cost effective. We don't have the funds to purchase a car or actual automobile to test this on. And also to maximize the input energy, the output energy versus the input. We want to maximize the amount of miles we get, miles per charge we get. This is tuning the controller to maximize how much regenerative energy we can get by using the capacitor. Some of the challenges that we faced were to make that regenerative braking efficient. We've never done that before. We are mechanical engineers, and that basically goes into recommending a multidisciplinary team. We're all in the mechanical option here, and it was a fun challenge for us to learn how to integrate all of these components to make it all work in a mechanical system while combining in electricals also. The budget constraints were also a challenge. We ended up going about over 30% budget, but that was because we had increased investments to try to get better parts, to try to achieve better speeds and more regenerative captured energy.
My name is Andrew Sean. I'm a senior in mechanical engineering, and I'm a minor in art. Now, to determine our motor power, we had a desired speed to reach about 45 miles an hour. And to figure this out, we used the equations to the top right, the 3 equations you see there. We took into consideration the total drag of the cart, the air resistance, and the rolling resistance needed to set the cart in motion. And we also added that to the total power required, the power to accelerate and the power to maintain speed. Through our calculations, we got about 10 horsepower minimum to reach 45 miles an hour. Some of the variables we need to consider while designing our cart was the voltage, current, range, and the cost of the cart. Now, the voltage is directly proportional to the RPMs the motor spins at, and an ample amount of current is necessary to generate the power necessary to put our cart to our desired speed. Now, we had to play around with these variables in a lot of different configurations to obtain a suitable range while maintaining our speed requirement. And also, to keep our costs down, we really had to pick our components carefully. And we decided to go with a Mars 019 DC brushless motor. It has 3 phases and is very similar to an AC induction motor. It's capable of generating 13.5 horsepower at 150 amps and a peak of 33 horsepower at 500 amps. Now please keep in mind that this is a very small scale. The entire weight of the cart is about 400 pounds with the driver, so there's not a lot of weight that you need to stop compared to a 2-ton car or like a big truck. We achieved about 10% efficiency, and we did this with 3 batteries running at 20% in contrast to 6 batteries at full power. We did this because we're still in our testing phase and we did not want to just put a giant surge of power the first time we went. And continuously we generated 12.3 horsepower for about 10 minutes. So how does this all tie together? Well, to give you a picture of what kind of technology is out there right now, this is the Tesla Roadster. It's on the market today. It has an overall driving efficiency of 88%, which is 3 times more efficient than any internal combustion engine, the highest being diesels. There are about 250 million consumer vehicles in the US alone, and we are responsible for 44% of the world's gasoline consumption. This translates to 360 million gallons daily, or 130 billion gallons annually. If 10% of the cars in just America were able to achieve a minimum of 10% efficiency gain, we would save 1.3 billion gallons a year. And with gas being $3 to $4 a gallon, the numbers really add up. With the implementation of our technology, we could help facilitate a shift to a much needed renewable and sustainable power source, and to help make our precious planet a better place. We really want to thank Progress Energy and the Department of MMAE for making our project a reality, and our advisor, Dr. Zhu, for all your help. Thank you.
Good afternoon, everyone, and thank you for attending today. We'd like to start off by thanking Progress Energy and our other sponsor, Power Grid Engineering, for their contribution for the idea and the funding for this project. Our project was the intelligent driving system for electric vehicles, and I'm now going to introduce the rest of my team, made up of 3 electrical engineers, James Keys, Mike Jones, and myself, Selena Martin, and our 1 computer engineer, Yazin Ganem.
What is an intelligent driving system? An intelligent driving system is a system that integrates into an electric vehicle, whether it be as large as a VW Golf or as small as a small electric Powerwheels toy. In a sense, electric vehicle is just a battery and a motor. What our intelligent driving system allows us to do is allows us to monitor the battery capacity, which is also like your gas gauge for electric vehicle. It also has a friendly user interface with touchscreen. So part of, for the electric vehicle we pulled up is the power system, in which we're using a 12-volt DC battery, which is going to power all our drive electronics and also the motors. A battery management system, which is going to have various sensors to measure the voltage and current so it can be read out and fed to the user interface. And a solar panel to also charge the battery when it is not plugged in or off the grid or parked somewhere. This is the battery we chose to go with. Was a 12-volt DC battery. It's a sealed lead acid. Our vehicle could be upgraded for greater range just by increasing the capacity, as long as it holds those same dimensions.
Hi, my name is Jim Keys. I'm an electrical engineer. I'm responsible for the motor drive electronics. I'm using a processor to monitor all those sensors and drive the motor. We put emphasis on the motor, the switching part of the motor, to make sure we do the most efficient switch as possible to minimize the losses in the electronics. And we're also implementing the 3 different modes of operation, so that when it's in the normal mode or performance mode, that whatever you put in for your gas pedal goes right to the motor. For the economy mode, we actually limit the amount of power that goes to the motor, depending on how much gas pedal you get. And then for we call it it was the economy mode. And the reason we're doing that is to limit the, when the battery starts to die, you don't want to make the battery electronics die completely. So I'm responsible for that, all that electronics.
We also have our power conversion block diagram, where you can plug our vehicle into an AC outlet of 120 volts AC and plug it into the converter that we have with the vehicle, where it will turn to 12 volts DC to charge our battery. This will also go to two power converters. We use the LM2596, which converts this 12 volts DC to 3.3 volts DC and 5 volts DC to give power to our several sensors throughout the vehicle, our temperature sensors for our battery monitoring system, and our voltage and current sensors that will be read and displayed on our intelligent driving system monitoring screen.
Hello everybody, my name is Yazin Ghanem and I'm a computer engineer. I'll talk to you about our user interface and some of the software designs that we did for this system. Our sponsor originally wanted to have in the specification a user-friendly touchscreen interface, and this is a mock-up of that. Basically, all these rectangles are just displays, and it's basically like a dashboard in your car. It shows you the speed and the fuel, check engine light, that kind of thing. On the bottom, there's going to be more information about your efficiency to show you how efficient your vehicle is. And you'll see this in a lot of modern cars. They'll tell you your instant miles per gallon versus your average miles per gallon. We wanted to do the same thing with electricity. On the left-hand side, those round rectangles are buttons. And you can see on the top, the user can actually select the 3 different modes that Jim discussed. So if you want to just drive normally, you select normal mode. If you want more power, you select performance mode, and there's no restrictions on the energy. It goes directly into the motor. Economy mode will restrict your energy to the motor, and it will cap it at a certain level. Now, all this is controlled between 2 different devices. One is the motor controller, and it communicates with this, the user interface. And if for some reason the system drops down to a certain level, the system itself will set the mode automatically. Like for example, if you're running low on charge, on fuel, you're automatically going to go into economy mode after a certain level. We want to thank Progress Energy for sponsoring us. Also PowerGrid Engineering for giving us the original idea and our original assistance. We'd also like to thank Dr. Ritchie for supporting us and giving us a lot of advice. And VNN Advanced Automotive Systems for helping us out with some of the aspects of the project.
Good afternoon. My name is Dan Beckett. I'm a mechanical engineering student here at UCF with an emphasis in material science. Today we're going to be talking to you about our senior design project, the solar-powered car cooler. According to the United States Energy Information Administration, over 17% of electrical usage in the United States in 2008 was used for cooling. This equates to about $78 billion spent. Now, with the steadily increasing cost of electricity and the dwindling supply and availability of fossil fuels, an alternative source of renewable energy must be developed. Additionally, because 20% of greenhouse emissions are estimated to come from residential home usage, the potential replacement energy source needs to be environmentally friendly as well as scalable from both large-scale commercial industrial applications to residential and even smaller. Now, both the private and the public sector have indicated their belief that photovoltaic cells potentially fill this requirement. In his keynote speech this morning, Mr. Vincent Nolan also iterated this belief. The United States government has instituted policy that lays out guidelines for the reduction of use of fossil fuels through the increased use of renewable energy. In response to this, the United States military has installed photovoltaic arrays at several installations throughout the United States. At the residential level, net zero homes, that is homes that use or produce as much energy as they use, are becoming increasingly attractive for potential home buyers for both economic as well as environmental concerns. Photovoltaic cells are also finding their way into the automotive market. On their Prius model of cars, Toyota is now offering a solar-powered car ventilation system. As you can see, photovoltaics are poised to take over a significant portion of the renewable energy market.
I'm a mechanical engineering student here at UCF with an emphasis on mechanical systems. The problem that we explored with this project was one that I'm sure everyone who is left in this room has experienced many times over. and that is that we live in the Sunshine State. If you happen to leave your car outside for maybe a half an hour or an hour, the interior cabin of the car can easily reach up to 130 or 140 degrees Fahrenheit. Now, because these are not ideal conditions for humans, we worked to design a system that would cool the car to 85 degrees Fahrenheit. Now, this system is powered by photovoltaic solar panels. It also is completely independent of the factory air conditioning system already installed in the car. And one requirement is, two requirements, it must run automatically with little or no operation required from the user. And it must also not obstruct the safe operation of the vehicle.
To accomplish the goal of our project, we decided to design a standard refrigerant-based AC system to cool the car to the requirement of below 85 degrees. The system is comprised of one photovoltaic cell, a battery bank, a compressor, evaporator, condenser, and a solar controller. The battery bank is composed of 6 Optima deep cycle batteries wired in a series parallel combination to achieve 24 volts. There's approximately 2.2 kilowatts of power available when the battery bank is fully charged. The compressor we have is a 12 or 20 volt compressor or 24 volt compressor that runs on R134A refrigerant, and it's a variable speed compressor. One of the big energy saving things we were able to do with this design is use a DC compressor instead of an AC compressor, so we avoided the conversion from DC to AC and the energy loss associated with it. The system is housed in the trunk of the vehicle. The batteries are on the side, and the compressor and evaporator are in the floor, the spare tire compartment. The way it works is the solar panel will charge the batteries when a car is sitting in a parking lot all day, and then toward the end of the day when you want to go home, you can set it to turn on and run for a half hour before you get to the car, and it will cool it to below 85 degrees.
The evolution of design, to improve the marketability of the system that we designed, there are several factors which need to be addressed. Specifically, technological and economic advancements. More efficient solar panels. As you can see in the lower right-hand corner, that is the current setup of the car. We have a solid polycrystalline solar panel. Ideally, we'd like to use the advancements being made with the film solar panels, which could be conformed to the shape of the car, so that you wouldn't have the overhang and it would be more aesthetically pleasing. Additionally, we have used deep cycle marine batteries, which, as you know, are very heavy, although they are the cheapest option at this point. Advances in the battery sector, more specifically lithium polymer batteries or nickel metal hydride batteries, would provide a higher energy density and would reduce the volume and weight associated with the deep cycle batteries that are currently in use. Our biggest hurdle for this project was establishing some kind of rapport with the manufacturers for the expensive and kind of niche components, specifically our compressor, which was the same compressor sourced in military applications for cool suits used by rotary aviators in the Army and soldiers traveling in Humvee, so they don't get overheated. Once that has been established, a better product flow to the end manufacturer would reduce costs and would make the product cheaper in the long run. From initial market research, there have been plenty of possible applications to the project that we've created. In its current form, it's in a car, but it can be applied to many different areas. As Dan had mentioned earlier, self-sustainable prefabricated housing, the net zero housing sector, they already have solar panels incorporated within the design of the house. Using our DC compressor, there would be no inversion of the input signal to power the compressor, so it would be more efficient. Additionally, residential and commercial cooling, you could use it in many applications. Server cooling, housing cooling to augment or supplement the already existing AC units there. Remote and military scientific outposts, this is probably the most promising application for our project. The military will operate in areas where they do not have a supply line which they can keep going for very long. They will rely on diesel generators. This way, they won't have to do that, and they can be self-sufficient as possible. Automotive cooling, as you've seen here in our application, and with the advent of the Prius cooling system, also could be applied towards K9 units that the police have. They won't have to run the car to keep the dogs cool, and they could use a solar panel and the system to cut fuel costs. So I'd like to thank everyone that had a hand in this project, Progress Energy for providing the funding, Masterflux for providing us the compressor, and additionally the consultation involved with implementing this type of system. B&H Refrigeration further provide consultation as well as man's air conditioning. Downriver Supplies supplied us much of our ancillary components involved with the system, and Dr. Marcel Illy of the MMAE department as our advisor. Thank you very much.
Hello everyone, my name is Andrew Bridges and I will be graduating with a degree in electrical engineering this May. And I am presenting to you today the solar-powered golf cart sponsored by Progress Energy. The goals and objectives for this project was to make a completely sustainable golf cart and increase the use of energy from the batteries within the golf cart. Now, because the golf cart is an electric vehicle, its motor does not leave a carbon imprint on the environment. However, if the power supplied from the wall outlet to charge the golf cart comes from a coal-burning or gas-burning power plant, then the overall system does leave some sort of carbon impact on our environment. The solar cells that we have put on the roof of this golf cart are capable of charging the batteries completely using sunlight, meaning there is no need to plug this golf cart into a wall outlet so long as there's light outside. Doing this will completely eliminate the carbon footprint placed upon the environment from charging the golf cart. Another part of the project was implementing an energy management system. We will have 3 modes of operation for our golf cart. There will be a high performance mode where the golf cart will be able to perform to the extent of its capabilities. We will have an economy mode which will slightly reduce the speed to increase the battery life of the golf cart. And we will have a power saving mode. And this mode actually is not a mode that can be chosen by the driver. It's a mode that kicks in when the golf cart is almost depleted in charge. And what it does is it's made to extend the life of the batteries as long as possible, allowing the driver to get the golf cart into an area that is well lit with sunlight so that it can recharge. Another thing that we will be doing in the energy management system is implementing a different method of speed control. When we received the golf cart, it used a resistive speed control, and we will be replacing this with a pulse width speed control. If you look on your left on the screen, you can see the approximate energy usage for the 2 different types of speed controls. On the top is the resistive, and as you can see, you waste a fair amount of the energy provided by the batteries in increasing the speed of the golf cart. Below that is pulse width speed control, and you can see that it greatly reduces the amount of energy used to increase the speed of the golf cart. Now, what is pulse width? If you look to the right of the screen, you will see a few examples of a pulse width modulated or PWM signal. Basically what we're doing is we're turning the golf cart motor on and off pretty quickly using that pulse. And the speed is determined by what percentage of that pulse is high versus low, or on versus off. If you wanted to go 50% of the total speed, then half of the pulse would be on and half of the pulse will be off. Now what will this do? With the motor off half the time, you're only using half the energy to excuse me, to achieve the speed of the golf cart. And this will extend the life of the battery greatly. By a slight reduction, by 10 or 15%, you can expect an increase in the battery life of the overall system.
Okay, my name is Nicholas Paperno, and I'll be talking to you about the monitoring system for this golf cart. Now, we'll have various sensors placed around the golf cart to tell us like what speed it's going at, how much current is being outputted, and what the voltage across the battery is. Now, to your, or my left at least, you can see a picture of what the inside of this golf cart looks like. At the very bottom between those battery sets, you can see all those wires converging, and that's our ignition switch. Our current sensor will be placed right about there and will monitor the total output of this golf cart. Now, a circuit board will be hanging from the bottom of the seat, and will have a small voltage sensor on it that will feed in our voltage, basically the voltage across the batteries, and reduce it to where our ICs can actually read it. Now we'll have a speed sensor which will also be placed right by the axle, and it's very hard to see in that picture. And that'll count the revolutions per minute that the axle is actually turning, and from there we can get speed, distance traveled, and whatnot calculated. Now there will also be a switch placed by the ignition that the driver will be able to turn and switch into the different modes of operation that Andrew mentioned earlier. Now once the voltage on the battery drops to about 15 or 20%, this switch will no longer be able to be used. Again, like Andrew said, the golf cart will automatically switch into the power saving mode. And in the mode of operation, and all these sensors will be hooked up to a display screen so the driver can actually see what is going on in the golf cart. They can monitor the voltage, the power being used, what is left, and whether or not they need to start charging or not.
And as you probably know, the use of display screens is becoming more popular, and energy efficient vehicles such as the Volt, the Prius, and the Leaf all use display screens. On the right you can see a display from the Chevy Volt, and the reason they use this is to provide the driver with information so he or she can know directly how much energy they are saving. So our programmable LCD module will serve a similar purpose. We will read information from sensors and display this information on the screen so the driver can know the energy that they are saving. Additionally, we will show the current mode of operation that we're in, the speed, the charge remaining, and the distance.
Now, we will be using two 15-watt polycrystalline solar panels to help charge the batteries. Through this, we can actually save the money. From a data sheet that we've accumulated from Progress Energy, you spend about an average of 12 cents per kilowatt per hour. And over a course of a year, if you charge once a week, you'll save about $50. Now, if you're charging it every day, you'd save about $350. Now, we took these calculations and applied it to some place like a golf course, which would have about 30 golf carts at least. And that would save roughly about $10,000, ten and a half, just every year. I would like to thank our sponsors, Progress Energy, our advisor, Dr. Ritchie, and Asley and Bob Rich for setting this up. If you have any other questions, we'll be at the back at our booth to answer them.
I want to really thank all the students and the teams for their diligent and work and their outstanding results and these things that you can take along with you in your career as you advance them.